check it.
Is that the one that was not there yet?
We did not, but let me grab it. It's probably fully delegated. It's uploaded?
Yeah,
So it's supposed to be. Might be good in between break times. It's like going to be. I'm gonna call people in right now. Did you call people in? Okay, I'm gonna grab some water.
So you have 13 minutes and then 5 for questions, a little bit of time. Great. Do you need any warnings or you have some thought?
Oh, there's lots of room.
Great. And I'll start by introducing myself.
I'm not sure, but I'm quickly.
So go over your, shall I start or you start?
I believe I just, Liz just told me last night that they got comments.
I don't care, I just don't want to throw the race up at the same time.
I'll let you pitch it. Go pitch it.
I don't know what I'm pitching. Yeah, no, that's good. Actually, it makes more sense when you do that, and then I would.
Yeah.
Good. How are you?
All right. How you doing? You gotta do your work.
Exhausted today.
Yeah.
That's okay.
Fridays are
It was
always
not
exhausting.
smart for me to be the chair of the last early session. That was the wrong morning.
You're not an early man, are you?
No, I was actually pretty good the last 6 days. Those were happening.
Yeah.
That's fine. So that makes more sense. It's all good.
Welcome, winter back.
Oh, yeah, that's the one.
This will come in and say.
But it's probably a window.
Are you sure?
Yes.
I'll be stepping in for as moderator.
For, sorry, oh. Wait, sorry, what?
Hannah's the
You mean
moderator.
WebEx?
Oh, yeah.
Yeah, the WebEx thing.
Oh, sorry, I got it. I did not know
see
that.
your confusion, and I'm like, no, you're fine.
Okay, that doesn't affect me. Got it. Okay, cool. Yes, you should be here. That's it.
I believe so, yes. That's what I'm just doing my assignment.
No, you should have.
No, I was Liz. And I want to advertise it, so it's all good. I would be very good.
No,
Very good. I didn't see it outside.
Yeah, no, I bet.
They have someone there. They have someone who does
Yeah, not like November.
It's a little early for Thanksgiving. In Colorado or November. So this one might actually. Oh, it would be in the.
Okay, good morning, everyone. Welcome to the final day of Inter+Stellar. I'm sad it's ending. I've had such a fun week with you all, but let's have a great send-off today. We have a lot of really interesting talks about early star formation and forming stars. I'm really looking forward to them. But before we get into our talks, we're just going to do a brief conference explanation announcement about the dusty universe. We've talked a lot about dust in this meeting. Personally, I am a big dust fan. So we're going to have Carl, who's the chair of the SOC for this meeting, kind of give a brief explanation about what the dusty universe is and what this conference is going to be like. So
Hi, everyone. So we're organizing this Dusty Universe meeting. It's the fifth in a series that we have nominally every 5 years. They started in 2003. Yes, we're late on this one. That's all my fault. So the idea is it's everything dust from planets to high redshift universe. And we're going to there'll be a bunch of invited overview talks as well as some contributed talks, but we're shooting for 300 people, I think. Most of the people will get posted flashes, have some non-talk at the meeting, so it won't just be a wall of talks. It'll be in Tucson in November. It's a nice time of year to visit Tucson. It'll be beautiful weather in the desert. Lots of astronomy there. We'll do tours of the Mirror Lab and at least Kitty Peak. And there'll be other options for doing tours. Let's see what else to say. There is a website up. You can just type Pandust 2025 and you'll find it, possibly with AAS. And if you go there, click on that form and sign up your email so we can keep you informed. We have not opened registration yet, but it will be. All the dates are on there. And I think that's it.
thank you, Carl.
And also talk to me again.
I'm Joel Green. I'm chairing the session. I'm yeah, let's start Young Stellar Object Friday. Okay, so our first speaker is Arpan Josh, and I will call up his presentation. I've not done this before because I just misplaced the. Okay, here we go. And play from start. And is your mic?
Good morning, everyone. And before I begin, I will thank the organizers for giving me an opportunity to present this work. So I am Arpan, and currently I'm a postdoc in Institute of the Radio Astronomy and Astrophysica, which is a part of UNAM. And there are my collaborators, Roberto and Charlie, and Johanan is also there. So yeah, let's begin. So my topic is like, this is like a small project that Roberto did, that I am doing with Roberto, which is like we monitored the coronate cluster of the Corona Australis with VLA and also KMOS with like in the same epochs. And I will just show you some of the results. And as it is like the last day of the talk, I have not kept all of the complex equations. I would only show some of the plots, and maybe I will try to convince you what we have got. So let's begin. So this is like the outline, the brief outline. I would just give a brief introduction and then about the observations, the results we got, and finally I will conclude. So let's have the small introduction. So I will thank all the previous speakers from last day. They have given us a very good idea about how the clouds form, and then from the clouds, all the prestellar core form. So my task became easy, and I will start directly from the young stellar objects when the clouds has collapsed from the cores and started forming the protostars and the Permian sequence stars. So these pre-main sequence stars on the YSOs, the young stellar objects as you can call, they are variables. They can be variable across all the different wavelengths. They can be variable in optical or infrared. They can also be variable in the 3.5 centimeter or the centimeter radio wavelengths also. So I guess most of you know about the optical and infrared variability. They can come from rotation of the stellar spots on the surface. It can be because of the small scale accretion variations, or there can be an extreme form of accretion variability, which are known as like FURs and XORs, which is like suddenly the accretion rate of these stars became elevated by at least two or more orders of magnitude, and it can remain for about years in the case of XORs, or for decades in the case of FURs. However, the most interesting, the other form of variability that we can see is in the radio, and that started with the VLA observations of the young stellar objects in around 1980s, and they found out that it emits weak radio emissions, and those radio emissions were like of two types. One was in thermal nature, which were generally found in the younger YSOs, like in class 1s and class 2s. And also the other form was like the non-thermal emissions, which were found in the more evolved YSOs, like in the class 3s. So, and then with all these observations and the theory came out, and the theoreticians predicted that for the thermal radio emissions, it is linked to the mass loss because of the accretion. But for the non-thermal emissions, it was linked to the gyrosynchrotron emissions because of the magnetic reconnections on the protostellar surfaces. So this was the theory that they put out, and in my project that I'm showing, I'll try to figure out whether that how the observations agree with the theory or not with our simultaneous observations. So what we did, we observed this corona cluster, our corona australis cluster, or which is also known as the coronate cluster. This is the location, and it's like located at very nearby at 130 parsecs. The reason for choosing this corona australis cluster was that it has the one of the highest density of YSOs at around 25 YSOs per parsec square, belonging to class 0 to class 2 stage. And also the other thing is that our work was easy because there was a previous work done by Don Peterson in 2011 using Spitzer data, who identified all the YSOs in this region. And also like Baobab Liu, he also studied this coronate cluster with VLA in a previous survey, and he marked out some of these radio bright radio sources in YSOs in that cluster. So during his study, he found out that the sources were variable, and it can be in some cases the sources were variable in the timescales of 30 minutes, or sometimes it can have larger variations, a time period of variations. So with that, we move forward and we observed the corona cluster, and this was like you can see the observations. With the VLA, the program ran from around 2012 to around 2015. And the vertical lines were the date of observations. And also we have this green one where we had this co-epoch observations with the K-mass of VLT. So we selected around 28 YSOs of this cluster, which were identified, as I said, from Peterson's study. And let's move on. And then what we did is that we observed and then we analyzed the data, and we found out from our sample of 28 YSOs, we found that around these 7 YSOs which had bracket gamma detections. It can in any form, like in emission, and also in absorption. So from this observations, we found out that these were like in these different stages. And when we matched with the radio observations, we found out that these sources have the matched radio observations, but the red ones, they have like the bracket gammas in emission, whereas in these two cases, the bracket gamma was found to be in absorption. And moving around, then what we did a simple task. We just estimated the flux of the bracket gamma sources, bracket gamma flux, and then plotted it with the 3.5 centimeter flux. of the corresponding flux. So in this case, what we did, we just made a very ultra deep image of all our VLA images and concatenated it and estimated the flux from that. And also we did the same thing with our KMOS observations, and this is what we got. We see a clear correlation between between the fluxes of the YSOs which were there in the class 1 stage, and here I should say the red ones represent like the class 1 stage sources, the greens are like the class 2s, and the blue one is like the class 3 sources. So here we can see that as the theory, as it was expected that because of the increased accretion in the class 1 and in class 1 stages, the accretions and the winds that are generated because of the accretion, it shocks the ambient medium and gives rise to this kind of radio emissions. So it was interpreted that in the class 1 stages we can have higher bracket gamma fluxes, and that would correspond to higher 3.5 centimeter radio emissions. But gradually as we move from class 1 stage to the class 2 stage, the accretion rate decreases. So this kind of what happens is that as the accretion rate decreases, this thermal radio flux, it would decrease. But in the class 2 stage, the magnetic field at the surface is also not developed properly. So the magnetosphere is not developed. So the non-thermal part of the emission is not still fully developed. So there would be, it is expected that there would be a decrease of the radio emissions in the class 2 stage, and that is what we can easily, and that we can see here. In the class 3 stage, when almost the disk is dispersed and there is no accretion, the only form of radio emission it can come out is from the magnetic reconnection events, and it should not be correlated with the bracket gamma emissions, if any bracket gamma detections, if we find any. So that is what we can find in the case of JVLA. So here I would pause a little bit, and I would say one thing more is about the picture is that in the class 1 and class 2 ISOs, the radio emissions are mainly dominated by the fluxes of the thermal radio emissions, whereas as we move on to class 3 stage, it is the non-thermal ones dominate. It's the interplay between them. So next up, what we did is that as we had the per epoch observations, we did the per epoch observation rate, per epoch light curves of the mass accretions and things, and the ionized mass loss rates. So what we found out, we did the co-epoch things. So what we thought is that we took like the 10-day gap as like our co-epoch observations. As you can see here, like it is almost around the same epoch, but not exactly the same epoch. What we did is that if it is like between 10 days, we considered it as a same epoch of observations. So in this case, for IRS1, which is like a class 1 OISO, we found one distinct epoch around as shown in the green, where we can see the high mass accretion rate correspond with a high mass loss rate, whereas in the other states it's below. It means it's less. Let's move on to here. We find a kind of correlation, but the situation becomes complicated in IRS2, where we can see it's that kind of anti-correlated. As you can clearly see, the mass ion loss rate is higher in a stage of low mass accretion rate, and it's vice versa. And then next, moving on to these are like case-by-case sources I am trying to highlight. And for Sgr A, which is like another class 2 source, here we cannot see all the variations are within error bars, and we are not able to constrain. It's like it's uncorrelated, the mass accretion and all. The other thing is that this Sgr A 43, which is like an class 1 source, but yeah, what we found interesting is that it has a very low mass accretion rate. However, the mass loss rate was 2 orders higher than that. So what we think about this source as maybe we have observed this in a very as the class 1 sources can be highly variable in accretions. Maybe we have captured it in a very quiescent phase when its accretion rate was very lower. So in that case, the jet part of the outflow rate of the magnet was very optically thin, and we are able to see the magnetosphere of the class 1 source, and that extra flux of the that we are estimating is actually which we believe is the magnetosphere of the class 1 source. But we caution and we say that we need further observations in radio to figure out that. With that, what we did, we measured the mass accretion relations with the mass loss rates, and we found out a same positive slope between them. And that's what the relations. We did it like in two ways. We grouped the epochs in which we had like the same epoch of observations, and we plotted it, and then we used our ultra deep image also to make the same fit. And in both the cases, we can see that we have a kind of relation between the mass accretion and the mass loss rate. And I don't know how it's not coming out there. I'm sorry, but yeah, what it happens is that, and I just have the last slide here, which is, and it's consistent with the other results like Rota and Garufi. And this is my last slide, and where we can see like for the high accretion rate tracers, the ratio between the mass loss to the mass accretion rates, it rises, means for the higher ones, the efficiency is lower, but it increases with the low mass accretion rate. Here we can conjecture two things. It's like for the higher mass accretion rates, if the jet efficiency is to be constant, the class 1 sources, the jets are mainly molecular in nature, or it can be like the sources, for the higher accretion rate sources, the angular momentum transfer is like anti-correlated. And these are the other things of my study, and I'm happy to take your questions. Thank you.
Questions for Armin?
Great talk. For the source in which like the mass loss rate is much larger than the accretion rate,
Yeah.
it will also be that we are observing the source post outburst, and now that the environment was still affected during the outburst. So environment is still the way it was during the outburst, but the accretion rate has gone down.
No, what we think is that as like a class 1 source, it can have a high variability in the accretion rate. We have captured it in a quiescent phase. So at that time, the jet core on that, which we believe, the jet core is like optically thin. So we are able to see the magnetosphere of that source. And from the radio emissions from that magnetosphere is contributing to the extra radio emissions. That is what we are hypothesizing. Yeah. Yes.
Yes, in the back of the car.
Great. Hi, thanks for the talk. I'm really confused by the anti-correlation between the accretion rate and the outflow rate. Do you have a physical picture in mind for this?
There are other studies also, like by like TP Green, not Joel Green actually. There was one study by him with class 1 sources, class 1 protostars. Like he took around a sample of 19 or 20. So in that sources also he did only spectroscopy, near infrared spectroscopy, and he looked at the bracket gamma lines with the H2 lines or the other outflow signatures. And there also he found out a kind of like this kind of correlations between mass accretion and mass loss is a kind of source specific. For some sources, it was like correlated, and some sources, it was like anti-correlated, and in some sources, it was like there was no correlation.
You have a feeling what's physically powering this relationship?
Yeah, what he anticipated, and which we are also agreeing with him, maybe the time scales between the mass accretions and the mass loss rates are different, and it's also specific for the sources. It's always not on the same scale.
Thank you.
I'll ask you, so by timescales, do you mean the length, the duration of the accretion, or the time delay between?
The time delay, maybe, yeah.
So what do you think it might be? Is there any constraint on that time delay?
Maybe for that, what I think is that kind of more sources we need, or some longer baseline surveys we need, which I don't have.
I mean, it may just not be reasonable.
I don't have any number on that. Yeah, sorry.
Okay.
other questions? We have a few more minutes. Yeah, so the reason I asked about the time delay is that the mechanism is very dependent on, I mean, where these changes start in the disk and impact how long it takes for it to show up in the tracer.
Maybe one thing is that it can depend on from where the accretion rate starts. Like for some cases, in some of the devices, it can be from the inner part of the disk, or sometimes it can extend to outwards also. Probably that can be one of the reasons. Okay. I'm not sure.
If there's no more questions, I have one final follow-up. Okay, so is there any big takeaway? I mean, is there anything you want the general population of YSO people to take away from the relationship you found?
Yeah, for the relations is that previously this relation that I found out here, it was mainly Yeah, this relation was mainly valid for the class 2 sources, and I had extended it to the class 1 sources, and that's what I found, that these correlations still exist for the class 1 sources also.
Perfect. Last chance for questions. Okay, then let's thank our speaker. You should come up. Let's see. Yeah, we're in no hurry. Sorry. Why am I not seeing the button to start the... Is it green? Yeah, the end result is green. Oh, thank you. Okay, then let's set this. And you can use 13 minutes and 5. Okay. There. Sorry. Okay, great. Well, our next speaker is Isha Nayak, and she will talk about JWST photometry and dust in the Magellanic Clouds. So take it away.
Hi everyone, my name is Isha Nayak. I'm an MPP fellow at Goddard right now, and I thank the organizers for allowing me the opportunity to present the work that our research group has been conducting, and all my collaborators for helping me reduce and analyze very complicated data for these past few years. So today I'm going to be talking about photometry and spectra that we got from Webb and how they reveal dust and ice in the small and large Magellanic Clouds. So why do we want to study low metallicity star formation? Star formation occurred in a low metallicity environment at the universe's peak star formation epoch. And so 10 years ago, I was a grad student, and I was putting together the APT files to study these 4 programs, inclusive of, WIKI 18, which is 1/50th solar metallicity, the small Magellanic Cloud, and NGC 6822, which are about 0.2 to 0.3 solar metallicity, and the Large Magellanic Cloud, which is about half solar. Because we know the distances to these galaxies, we know the luminosities of the sources that we measure. And with Webb, we're allowed to maximize statistics. We go from hundreds of sources in Spitzer and Herschel observations to over 1,000 sources in just a single image. Webb also has excellent synergies with ALMA and HST, so we are really able to do Milky Way-like studies outside our galaxy for the very first time with Webb, and that is very exciting. So here's a Spitzer image of the Large Magellanic Cloud, and we are interested in targeting superstar clusters because superstar clusters were the predominant method of how stars formed about half the age of the universe, 6 to 7 billion years ago. Galaxies like the Milky Way form dozens, if not hundreds of stars every year. However, the star formation rate has decreased over time, and we want to understand why. Superstar clusters are massive young clusters which contain thousands of OB associations within a small, compact region. Milky Way has Westerland 1, which is a superstar cluster about 3 million years old, and highlighted here is the 30 Doradus region of the Large Magellanic Cloud. The R136 superstar cluster in 30 Doradus is several million years old, and the entire region as a whole has gone through several starburst phases in the last 25 million years. With our Webb observations, we confirm that the LMC is host to another superstar cluster in the southwest corner called the N79 region. We call this superstar cluster H7297. It's based on the Herschel coordinates with which it was first observed. This region is less than 100,000 years old and is undergoing its first starburst phase. On the left here is the ERO team release of NIRCam image of the R136 superstar cluster and the surrounding 30 Doradus region. On the right, I'm showing the NIRCam observations of the N79 superstar cluster. So, like I mentioned before, 30 Doradus has undergone several starburst phases, and N79 is going through its initial starburst phase. So we see similarities and differences. With NIRCam, we're able to observe protostars, thousands of protostars that we were not able to see prior to getting these web observations. Here's the full NIRCam image. So with NIRCam, we observe over 1,500 protostars in the region showed here. The most massive stars are forming at the gravitational center of the superstar cluster around here, and the lower mass stars are kind of throughout the entire region along the wispy structures seen. So with NIRCam, we can get information about early and late stage star formation. With this MIRI image here, which is slightly smaller than the NIRCam footprint, we really see the most embedded sources in the region. So this MIRI image shows several protostars. We see bow shock-like emission as well as whirlpool-like emission down here. So there's a lot of interesting things happening within this MIRI image. There are 102 YSOs in this footprint that we identify with MIRI spectroscopic imaging as well as MIRI photometry. The NIRCam data shows 1,500 protostars in a footprint that's larger than this, and with the NIRCam image, we were finally able to call this a superstar cluster and not just a superstar cluster candidate. In black and white here, I show the MIRI F1000 wide filter, and all these colors represent YSOs in a different mass range. There are 13 YSOs that are greater than 8 solar masses shown in this footprint. 12 of the 13 YSOs greater than 8 solar masses, which is the pink circle, are kind of at the gravitational center located right here. The more massive YSOs seem to be forming along shell-like arcs, which I highlight in red dotted lines, and the less massive YSOs are kind of all over forming in the wispy pillar-like structures. This is consistent with observations done with RCW 120 as well as modeling done by Walsh et al. I also want to highlight our observations of NIRCam observations of the Small Magellanic Cloud. On the left here is a 4-colored combined image, and on the right is just the F335 image in black and white. So it's the PA emission. With NIRCam, we discovered thousands of low mass YSOs, less than 5 solar masses, in the footprint that we got. And with Webb, we are able to go 2 magnitudes deeper than Hubble, so we actually identify protostars that we did not see with Hubble with our NIRCam observations. We also have MIRI observations of NGC 346. MIRI traces the cooler dust and gas, and we really see where the deeply embedded stage 0, stage 1 protostars are with the MIRI observations. Here is the MIRI F770 wide filter, and with MIRI we find over 800 YSO candidates, which have also been flagged with NIRCam. All these different circles represent how many color magnitude cuts these YSO candidates passed. So you'll notice that especially the red circles are those that pass 7 to 10 tests, and the yellow diamond is those that we fit with the SCD model. So where the red circle and the yellow diamonds are the candidates that we are really sure that these are indeed protostars that are deeply embedded protostars, very young. You'll notice that the redder and more deeply embedded sources that we are confident of kind of lie along the filaments. We also have MRS spectra. We made 4 pointings in the Large Magellanic Cloud in the N79 region. So the N79 region consists of 3 GMCs, the East GMC, the West GMC, and the South GMC. We have an additional 4 pointings of MRS in the SMC, and we determined where to point MRS based on previous Spitzer, Herschel, and ALMA observations. So first, I'm going to show you what we see with our MRS observations in N79 East. Here is the Spitzer IRS spectra from almost 2 decades ago, maybe. And we see that what we thought was a single YSO has resolved into 2 YSOs, which we called YSO Y2 and Y3. Here I show the neon 2 cutout of the MRS cube and what YSO and Y2 and Y3 look like in the cutout cube. So just as a note, the MRS field of view, what we're looking at distances of the Large Magellanic Cloud, is essentially the size of the trapezium in the Orion Nebula. So we really can resolve individual stars at extragalactic environments with the Webb data. So YSO Y2 here is the more dominant and more massive source. However, YSO Y3 is the youngest source in our entire MRS observations, and we know this due to the deep absorption lines that we see. Here I show MRS channel 2 and channel 3 spectra of YSO Y3. We have the CH3OH absorption line at 9.7 microns, as well as the CO2 absorption line here. The CO2 absorption line is actually a combination of 3 different absorption lines. At 15.1 micron, we have the CO2 and CO, and 15.25, you have the CO2 plus H2O, and then you have the broad shoulder based from the CH3OH absorption lines. And from these absorption lines, we estimate that this source is less than 10,000 years old, which is very young. So next, I want to show you what we see at the superstar cluster, which is located in the N79 South GMC. We also have the Spitzer IRS spectrum of this source, but with MRS, it resolves into 5 individual protostars. And once again, I'm showing the neon 2 cutout on the top right there. YSO Y4, just by itself, is 40 solar masses in size and over 500,000 times more luminous than the sun. Channel 1 and Channel 2 spectrum of YSO Y4 shows several emission line structures, and we see forbidden lines of iron, argon, neon, and so forth. This is the Channel 3 spectrum of just YSO Y4. I want to highlight the neon 2 and neon 3 lines because we need at least 41 eV to ionize these lines, which means there's a high energy UV photons from either the central star or from shocks in the region ionizing these lines. We also infer a mass accretion rate from the Humphrey 7-6 emission, and we estimate it to be 0.02 solar masses a year. So which means every 50 years, this single protostar right here is accreting an amount of mass that's equivalent to the sun. We have 4 MRS pointings towards NGC 346 shown here. From these 4 pointings, we resolved 9 individual protostars. Here are spectra of 5 of the 9 protostars in NGC 346. So once again, even in the SMC, we see a very rich spectra in all the protostars for which we have spectra for. I do want to highlight the 15.2 CO2 absorption line. We only see this in one source in the SMC. And this absorption feature is not as strong as YSO Y3 in the Large Magellanic Cloud. This could be because the source is a bit older and therefore not as embedded, so you don't see the absorption lines to be as deep, or it could be that this source is also a lot less massive. It's about 7 solar masses in size, as opposed to the YSO Y3 and N79 is about 18 solar masses in size. So I'm not sure how much time I have left. Oh, okay. So in conclusion, we have NIRCam, MIRI imaging, and spectra. We're able to go 7 magnitudes deeper than prior surveys of the Large and Small Magellanic Clouds. In N79, we identify over 100 YSOs with MIRI and over 1,000 with NIRCam, with the most massive being concentrated at the gravitational center of this superstar cluster. In NGC 346, for the first time, we see protostars as low as half solar in a low metallic environment of 0.3 solar masses. And MIRI spectroscopy shows similar and different absorption and emission lines between the 2 regions, which we're still working on modeling and getting more information from. So that's it, and I'm happy to take any questions.
Questions? All right. Let's start back here. Mordecai.
Is there any evidence on whether these very bright YSOs are actually multiple systems. You have velocity resolution to say anything at all about that?
So you mean if they're possibly binaries?
Yeah, I mean, you know, stars like this are almost always binaries in the Milky Way.
Yeah, so we don't think so. So in this image up here, you seem really close, but they're still not binaries. Like
I was thinking about single line spectroscopic binaries.
Oh, I don't think we have the data to do that.
Resolution.
What is it?
Be like 100 kilometers a second.
Yeah.
You ought to be able to see a line shift in the single line spectroscopic binary at 100. Because these things are massive. They must be whirling about.
Yeah, I don't think that's something we can pull out from the data we have.
Okay, thank you.
Let's see. Okay, so go ahead. Yeah.
Slightly more of an ignorant question, so I apologize. But I'm getting a little hung up on this term superstar cluster. It seems kind of different than what other people have been talking about. I was wondering if you had a mass of the cluster that's being formed here in the LMC, and then what kind of we're talking about when or how you're defining superstar cluster as opposed to just a star cluster.
Yeah, so the definition is the CO2 mass is above 10 to the 5, preferably 10 to the 6 solar masses in size. So for the South GMC here, we have non-10 or ATCA observations that show it's about 10 to the 5 solar masses of CO in this region right here. Another definition is that you just have like a lot of protostars in a compact space. So with NIRCam revealing over like 1,000 sources, that means it's like a really active star formation region. What else? There are definitions, and this superstar cluster is kind of on the lower end in comparison to 30 Doradus. So 30 Doradus, you know, the luminosity is maybe 1 to the 7 solar luminosities, right? So it's on the lower end, but we think it's ramping up its star production rate. And we see that by comparing H-alpha observations and counting YSOs. So we can measure, like, has the star formation increased for the past few million years? And it has. So all these point to it being a superstar cluster.
Let's Liz, and then.
Your spectra are so beautiful. I
Thank
could
you.
cry. They're awesome.
There is so much information in the
I love
spectra.
And I have several questions about them. I'll keep it to one, especially in the case where you have that heavy absorption feature in the youngest one ever. So that's a point where maybe you could get kinematic information, not necessarily to answer Mordecai's question, although maybe to also answer Mordecai's question, but just to see if you can observe any of the kinematic accretion coming onto these protostars or any of the feedback that the protostars are exerting on their environment. Is there any possibility of doing that?
Yes, so it's definitely something we're interested in looking at. So there's PAW emission, there's ice absorption. You could do cloudy modeling and just the like forbidden lines. And so this is just the initial paper that I'm presenting. So there's a lot of work to be done, and maybe we can. It's something definitely to look into.
It's like a dozen papers.
Yeah.
You used the Humphrey line to get the accretion rate. Could you just, I didn't know that line had been calibrated to measure accretion. Could you just talk a bit about how you went through that process? And after that, I was wondering if you used Passion Alpha images to compare, because that's also, you can use that for the accretion rate as well.
So we did not use Passion Alpha, but as for the Humphreys line, we kind of just so the way we looked for lines is we kind of fed our code a line list and mashed it to the nearest line. And we are pretty sure it's the Humphreys line because it shows up, where it's not noise, it shows up in multiple different YSOs, and there's really nothing else it could be in terms of the line list that we fed it. So we're pretty sure it is the Humphreys line.
How did you convert that line luminosity to an accretion rate?
There's a formula. I forget whose paper.
Questions about where that formula
Okay,
comes from, but we can get into that later.
Yeah, it's cited in my paper whose formula it is. I don't remember on the top of my head.
Okay, no problem.
Yeah.
Thank you.
Sorry, we just keep, go ahead.
Yeah, okay. You mentioned you are still analyzing the features, but it's just wondering, what is the temperature and mass of these ice? Also, is there any meteoricity dependence in these objects?
Right. To temperature, we'd have to do further modeling to infer the temperature, like as opposed to metallicity differences. So that's another difference that could be between what I show here and what the SMC ice absorption feature shows. It's not as deep, right? So that also could be due to metallicity in addition to age and
maybe UV addition fields.
Yeah.
Because of this low extinction, maybe.
Yeah, it's hard to disentangle all these. You definitely need to like do more intensive modeling than what we've done in these initial papers so far.
Okay. Okay. Let's go to the next speaker. Our next speaker is Laura Lankage, who I'll call up a presentation first. Sorry, this is clumsy. Okay. We'll talk about molecular gas properties and young stellar objects in NGC 346. I will make sure that I get this on. Oh, I'm still in slide mode. Yeah. Oh, there. Thank you. Okay, great. Take it away.
Thank you. Can everyone hear me? Great. Okay. Good morning, everyone. Thank you all for being here. Thank you to Liz and the organizers for this really wonderful conference. I'm very happy to be here to present some of the work that our group has been doing on the star-forming region 346 in the Small Magellanic Cloud. My title is different from what is in your little abstract book. Apologies for that, it's still the same content. And though it says molecular gas properties first, I'm going to talk about YSOs first and then go to the molecular gas. All right, so Isha already motivated really well why we are interested in looking at star formation and the ISM in the Magellanic Clouds. This is an image of the Small Magellanic Cloud, which we've already seen earlier this week. But the SMC is a really nearby dwarf galaxy. It's about 61 kiloparsecs away, and it has a low metallicity, about 0.2 solar. So it offers an excellent opportunity to study stellar populations and the ISM and their relation to each other in a low metallicity environment at subparsec resolution. So the region that we're particularly interested is highlighted here. It's the NGC 346 or the N66 region. And we've already seen this image, but I have to show it again because it's so beautiful. This is a James Webb image combining 4 of our filters, the F200, 277, 355, which traces the 3.3 micron PAH, and F444. So the NGC 346 region is the largest and brightest H2 region in the SMC. As we've already heard, it contains about 800 young stellar objects and young stellar object candidates. It also hosts thousands of pre-main sequence stars and about half of the SMC's confirmed hot star populations like O and B stars. It's a really actively star-forming region. There's a lot going on here, and so we'll just get into some of what we've learned from James Webb and ALMA together. So with the James Webb observations that we have, we've done source detection, PSF, and aperture photometry using Starbug 2, which is a photometry tool written by Connor Nally. He's a PhD student at the University of Edinburgh, so I just want to advertise his work a little bit. His code does estimations of diffuse backgrounds, and it performs really, really well with James Webb observations, where we see a lot of this wispy, diffuse, dusty emission. And this is just an example here how his code performs in estimating the background, which is then subtracted from our images, and then we perform PSF photometry on those background subtracted images, and the code can now do this for both NearCam and MIRI, and it performs really well. So here's an example of one of our color magnitude diagrams combining the F115 and F200 data that we have. And just to give you an idea of how many sources are detected in that image that I showed on the previous slide, We have over 100,000 point sources to work with, and that's what's shown in this color diagram here. So here I have the F115 minus F200 color as a function of the F115 filter, and there are many different stellar populations that we can see here. Here we have the upper main sequence. We see red giant branch stars. Here is the red clump. And then these blue, variously shaded blue diamonds here are our young sources that we identify. So we have pre-main sequence stars, and then YSOs that have a Paschen alpha excess, and those without a Paschen alpha excess. And this is a tracer of accretion onto young stars, and we get that from this F187 narrow filter here, which is one of 6 NIRCam filters that we have. So we also have Miri photometry in 5 filters. This is another beautiful image combining all 5 filters here, showing what the NGC 346 region looks like, combining those filters. And so we combine all of the filters that we have in all sorts of various color magnitude diagrams, which you can see in Nolan Habel's paper here. This is just one example of one of our Miri CMDs, combining the F770 filter with the F100 filter. And again, here we show the YSOs and the pre-main sequence stars, and these yellow diamonds are sources that we fit with SED models and that have very good matches. So these are sort of our high reliability YSOs in this region. And we have upcoming papers that will do a much more detailed analysis of the young stellar populations in this region. That should be coming out soon. So with these various combinations of JWST filters and the photometry that we've done, we establish color selection criteria and perform SED fitting, removing contaminants such as background galaxies and such things. And we end up with a candidate list of 833 YSOs and YSO candidates. In addition to the photometry that we have with NIRCam and MIRI, we also have various spectroscopic data. Isha already showed some of the MRS data that we have in NGC 346, but we also have near-spec MSA observations. We have 2 epochs of MSA data. This is showing our first epoch where we observed pre-main sequence stars that were selected from HST to have an H-alpha excess and to therefore be still accreting objects. From those HST data, ages of these pre-main sequence stars are also estimated. And so we've selected sources to observe that are up to 30 million years old. And we observe them with the MSA. And this is just some of the data that we've obtained that is published in Guido De Marchi's paper that just came out at the end of last year. So there's a lot here, but what this is showing, these first 7 spectra are what were determined to be accreting pre-main sequence star from HST observations. And then as a control, here we have 3 spectra of main sequence stars, just to show that our HST or the HST selections of these objects are indeed picking up accreting young objects. So there are various hydrogen recombination lines indicating accretion. There are many H2 lines indicating that there's still natal material that is surrounding these objects. And when we look at the main sequence spectra, we don't see any of those features. So this is a really exciting paper because what this is showing is that at low metallicity in the Small Magellanic Cloud, pre-main sequence star as old as 30 million years are still accreting. And this is, these accretion periods are longer than anything that has been observed in the Milky Way. And this is interesting because we might have expected that in such environments that disks around these young stars wouldn't be able to survive as long in these sort of low metallicity, harder radiation field environments. But what we're finding is that they are indeed still accreting. And so if you're interested in that, you can take a look at Guido's paper. And we have epoch 2 observations where we've observed YSOs that were selected from the JWST photometry, and that's work in progress. We see all sorts of interesting features, ICEs, and so that's something that's coming up. All right, so that's kind of what we see from the results stellar populations in the young stars in this region. So now we're interested in knowing what does the CO gas look like in this region. So for this next part of the talk, I'll be referring to ALMA observations where we have archival ALMA observations where we have 12 CO1 to 0, 12 CO2 to 1, and 13 CO2 to 1 data at about 0.6 parsec resolution physical scale. So what does that data look like? So here I'm just showing a peak signal to noise ratio map, just so you can see the full extent of the data. And this is the 12CO 1 to 0. So you might be able to recognize lots of these wispy filamentary structures that we see in the James Webb data. So there has been one study that was published using these observations where they looked specifically at the 12CO 1 to 0 and the kinematics of this data to see what is going on kinematically in the region. So specifically, this study focused on this two filamentary region up here. And what they find from the kinematics is that these two filaments in PV diagram space appear connected, and one of these filaments is blue shifted while the other is red shifted. And they sort of connect at this region here, where from Spitzer, there's a known intermediate mass YSO and several or many pre-emitting sequence stars. So this appeared to be colliding filaments, where at the intersection of this collision, there's lots of young star formation that's happening. So the study focused specifically on this region. So what we were interested in this work is to look at the molecular gas across the whole region and see what that looks like. Okay, so and for the rest of the talk, I'll be showing here this F770 image that we have from JWST Mary, which traces or includes within the band the 7.7 micron pH feature. And overlaid at the moment are the 12CO 1 to 0 contours. We also have 12CO 2 to 1 data, as I mentioned. So this is another peak signal to noise ratio map showing what that looks like as a comparison to the 12CO 1 to 0 and the F770. And then we also have 13CO 2 to 1, and that's what that looks like. And just a note, the scale bar here corresponds to 5 parsecs, so just so you have an idea of what we're looking at. Oh, and I forgot to mention this is the ALMA beam. So what we did is we took these 3 CO tracers and sort of did cloud identification. I won't go into the details of that. I'm not going to show any plots, but we basically use AstroDendro and then a subsequent clustering algorithm that identifies independent structures from the dendrogram tree. And so when we have sort of our cloud catalogs, we measure the line widths, sizes, masses, and then look at some relations like the size line width relation, which I'm showing here for the 12CO 1 to 0. So there's a lot going on here, so I'll walk you through. This gray line here is the Milky Way relation from Solomon 1987, which has a slope of about 0.5. So the line width depends on the size of the cloud to the power of 0.5. And then overlaid, we have some relations that have been found in the 30 Doradus region from Wong 2022, which is this dashed line here. And then from a subsequent study from Alex Green, 2024, this dotted line corresponds to the relation that was identified in a collection of GMCs in the LMC. And so overlaid in colored symbols are our results from NGC 346. In diamonds, I've just colored CO clouds that are associated with YSOs, and in green, those that are not associated with YSOs. So what we find for 12CO 1 to 0 is a size line width relation that is consistent with the Milky Way. When we perform a fit, we get a slope that's in line with what's been observed in the Milky Way. We also find that most of the CO clouds are associated with YSOs. It might be a little hard to see, but each of one of these little green circles is a YSO or YSO candidate from James Webb. And so you can see those lie along these filaments. But we also find no significant difference in cloud properties that have YSOs or don't have YSOs, at least for the 12CO 1 to 0. We also look at sort of the boundedness of the cloud. So the y-axis now is showing the square of the line width divided by the size. And on the x-axis, we have the mass surface density of the clouds inferred from the 12CO 1 to 0 luminosity. This solid line here corresponds to virial equilibrium, and the dotted dash lines, I keep saying dotted, dash lines correspond to pressure of clouds in virial equilibrium supported or bounded by external pressure, lots of words. And again, I've separated these with clouds that have YSOs and those that don't. And we see for 12CO 1 to 0, clouds sort of lie around this area of virial equilibrium. Some clouds have a higher size line width parameter and are consistent with being bounded by these high pressures of about 10 to the 5 to 10 to the 6. Okay, so now I'm going to show the same sort of set of plots, but for the 12 CO2 to 1 and then 13 CO2 to 1. So now the contours here correspond to the 2 to 1 transition, and that's what we're showing in this figure here again. Now we're comparing to an additional study from 2022 looking at NGC 602, and that's this relation here. So that in the 12 CO2 to 1, our clouds have a slope that's consistent with the Milky Way, but a higher normalization, indicating potentially enhanced turbulence in these regions. But we again find no significant differences in the sizes or line widths when we compare the clouds with and without YSOs. When we look at this sort of like boundedness plot again, we see that the 12 CO2 to 1 clouds are not in virial equilibrium, but they're in sort of, if they are virialized, they're in various states of pressure bounded equilibrium. And again, no real difference for clouds with or without YSOs. And finally, we have the 13 CO2 to 1. This is my last slide. Here we find a much steeper size line width relation for the 13 CO2 to 1 clouds, which has also been found in 30 Doradus in other LMC GMCs. And here we actually do find statistically higher line widths for clouds with YSOs versus clouds without YSOs. And I'm out of time, so I will just leave this up here, and I'm happy to take any questions. Thank you.
Questions? Yes. Yeah, sure. Thank you very much for the talk. This is great. It was really cool seeing the photometry in such a very distant region. I'm just wondering what sort of ability you might have to detect like different ages using that data. Is it possible to like tell a 5 or 10 million year population apart? And if so, can we get like star formation histories of these things, or do we need to do more to get to that point?
Yeah, that's a really good question. Sorry, I'm just trying to scroll back. So in the Hable et al. 2024 paper, we do have versions of these plots with isochrones overplotted, like the parsec and MIST models. And I think you can actually distinguish ages. So in another galaxy that's part of the sort of set of galaxies that we study that Isha already mentioned, the 1Zwicky 18 galaxy, which is 18 megaparsecs away, there is a paper that has come out that has done an analysis of the star formation history of 1Zwicky 18 using JWST photometry. That paper is Bortolini et al. 2024. So we've done it in 1Zwicky 18. We haven't done it for any of our more nearby objects yet, like NGC 6822, which is about 500 kiloparsecs away, or the Magellanic Clouds, but we should be able to do that.
Thank you.
Mm-hmm.
Really great work. What's going on with these extended accreting stars? Do you have ideas about what's going on?
That is a really good question. We're not sure, actually. That's something that we're thinking about and trying to understand more. Yeah, I don't know. It's the answer. If you have ideas, though, let us know. Oh, we would be happy to hear them.
Let's see. Okay. Yeah, Matt.
Well, just kind of combining the previous two questions of how do we know the ages of these, at putative accretors with the H alpha lines? I mean, how do we know they're 30 million years old?
So I will first say, in this 2024 paper, there's a whole section on the ages that will explain it much better than I can. So I will refer anyone interested in that there. But basically what was done in the previous papers working with the HSC photometry, they looked at the basically HR diagram, like temperature and luminosity of all the like HSC detected sources, and use isochrones to estimate the ages. There is a whole discussion in the paper on the uncertainties of estimating ages in that way at these low metallicities. And the argument is that, I'm going to get this wrong in the paper, but the conclusion is that the uncertainties should be less at lower metallicity because of how the time scale of stars to go from the Hayashi track to the main sequence at low metallicity versus like Milky Way. So there's a whole discussion in the paper there. That was something that the referee had lots of questions about. And so we tried to do like a careful, detailed discussion of why we believe those ages to be correct.
Mordecai?
So your molecular clouds are in a highly dynamic environment. They're clearly collapsing quickly. You can tell there are lots of stars forming. They're subject to intense feedback. Why would we think that they're in some sort of pressure-bounded equilibrium rather than in a very dynamical, either freely falling collapse or dramatically impacted by feedback expansion sort of situation?
Yeah, that's a really good question. I agree with you. This is a really dynamic environment. This was alluded to in Peter's talk the other day, that the NGC 346 region is also, there's all sorts of things going on. That everything is rotating, spiraling inwards. It is very dynamic. So I guess I wouldn't really say that these are in equilibrium. The figures I showed before were kind of just to guide the eye of like where these things are. But
not be the best theoretical model to overlay.
Fair, okay. Yeah, I would love to hear maybe more of your thoughts afterwards. Thank you.
Karan and then Amy.
I just wanted to add to the discussion about the ages, that the absolute certainty on those ages is always very poor, factor of 2 or 3. It's the relative age that's important. And the fact is that when you go to low mass star forming regions, you never see accreting stars in that part of the HR diagram. That's the point. The absolute age may not be really 30 million years, but there is a huge difference in the position of these stars on the diagram compared to low mass star forming regions.
Right, yes, these are much closer to the main sequence and they're still accreting. Yeah, thank you.
Yeah, I just had a question following up on Mordecai's. Did you look in the CO data at the moment 1 map, basically the velocities instead of the line ones? Tease out these velocity patterns, rotation, etc.
Yes, yeah. So I haven't shown them here because I'm still figuring out that everything is correct. But that is something that we're looking at, and that will be in the paper that is currently in preparation. Yeah, thank you.
Let's thank our speaker. And our next speaker will be Bina Mina, and I will find your presentation.
Just do the play here. Play.
Perfect. Thank you so much.
Actually, I have to go back.
Nope, that is not. Yeah, that started. Yeah. Oh well.
No, the last slide.
Huh.
Am I audible?
Is your green thing on, and you want to put that in a? Do you have a place to put that?
That?
No, this.
Okay. This I don't. Ah, okay. Thank you.
But you shouldn't have to hold it.
I know, but I don't have pockets. It's fine. I'm
okay.
good. Thanks.
Thank you.
Thank you. Hello. Good morning. Good morning, everyone. My name is Bina. I'm a postdoc here at SGSEI, working with Dr. Peter Zeidler and a bunch of international collaborators. If you remember on Wednesday's talk, Peter had introduced the first brown dwarfs that were found outside Milky Way in NGC 602, which is the target of my study and the talk today. Which is a young cluster in small imaginary cloud. I'll talk about that a little bit later, but let's revisit young stellar objects. Young stellar objects, this is basically the earliest stage of star formation, and the evolutionary stages go like this. Like first you have the molecular cloud, which under the gravity or turbulence collapses and form this very dense cold core. We call that the pre-stellar dense core, and that's the earliest stage. And then you have a class 0 stage, which is where the pre-stellar core forms and starts accreting. The core is still very extremely embedded under a thick envelope of dust and gas, and the overall the black body like SED looks like very cold, about less than 70 Kelvin. The mass of the pre-stellar core is less than the mass of the envelope, because again the mass of the is huge and dense. At that point it's accreting class 1 stage, where it forms the disk and it's accreting, but at the same time also creates outflows and jets, all sort of things, and that's called class 1. The temperature of this the whole black body looks a little bit higher, 70 to 650 Kelvin, and at that stage you have formed the star, which has a mass greater than the envelope, the mass of the envelope. And then you have the third stage where we have class 2 and class 4 objects. Class 2 is where you have the disk and it's not accreting as much, but it has formed the protoplanetary disk. And then you have class 3 where you start to make all these planets, Jupiter mass planets, and so on. So just an introduction of all these type of YSOs. And now to NGC 602, which is the target here. NGC 602 is a young star cluster right here in the wing of the SNC. And then if we zoom on in this wing region, this is an optical image that has been taken by someone's camera in the backyard. Beautiful. And then finally, we have very latest JWST image using NearCam. It's beautiful. All these stars are visible, and then you have a bunch of galaxies. A lot of galaxies visible as well. So why this target is important, as Isha and others have already discussed, a lot of targets in LNC and SNC are, particularly SNC is a low metallicity star cluster. It's about 20% of the Milky Way or solar neighborhood. And so it's very important to study how stars form in low metallicity environment, because particularly for NGC 602, with this metallicity, it is still forming star and has a mass budget of comparable to Milky Way's Traveler 14 cluster, which is in Orion Nebula. So that's very intriguing, and we want to know how stars form, especially the earliest stage of star formation in this low metallicity environment, and also that gives us a window of star formation in the early universe when the metallicity was extremely low. So so next is for this talk, I'll be focusing on the young stellar objects population, which is YSOs. So let's compare what has been done before JWST. There is an image of Spitzer and optical ACS image from HST. And so Carlson 2007 and 2011 has found a bunch of YSOs, about 40 YSOs in NGC 602 at different evolutionary stages. These YSOs are highlighted in these circles, but you can see the Spitzer resolution and the earlier the JWST image that I have shown, the drastic difference over there. The resolution is about 20 times, I think, more for JWST. So what they had claimed is that the 70% of, more than 70% of the YSOs that they have found are probably multiple sources. So yes, they were resolution limited, and that's why there were higher uncertainties on the type of particularly the characterizing the YSO population. And that's why we went ahead, actually Peter's program, and took images using NearCam and MIRI in all these filters to properly characterize the YSO properties at high, extremely exquisite resolution with JWST. So we have all this data. The goal is to first identify the very nice YSO population and the pre-mean sequence stars in NGC 602, and then move forward and learn how the OB stars at the center, the massive OB stars, they are affecting the star formation in these galaxies and affecting the properties of YSOs. Sorry, not galaxies. I work on galaxies a lot of times, so this is the first time I'm working on a cluster. In the cluster, and then how the properties are affected by the radiation from the massive OB star. So first thing first, so Peter had presented the NearCam images on Wednesday about how he found with NearCam images the brown dwarfs and all that. I will be focusing on NearCam plus MIRI. So I was in charge of the MIRI observations, where I started from the reduction, photometry, and then just looking at the data. So the first thing I found was when I was just looking at the image, there was an interesting object that I found. I'll talk about that in a bit. But again, this is the NGC 602 NearCam beautiful image. I want to introduce this star here. It's called SK183. It's a very massive O3 type star. So when I was looking at these are near-cam images. So not looking at that for now, but when I was looking at the MIRI images, this is an RGB image using 3 of the MIRI filter, and I don't remember which ones, but 3 of the MIRI filter. And then this, because this is a very massive O3 star, it's not as bright in mid-IR. We can, it's like small here, but then I also see this like large diffuse, a sort of mid-IR extended emission. And that made me curious because I compared that with the MIRI images, near-cam images, if I can see that object. So right here where the cross is, this is where this object was seen in MIRI. This is MIRI. I tried to do a PSF subtraction on digital images. It's not very good, so don't judge me. But the idea was to just see if I can see any emission in the IR, near-cam images, and I don't see anything. And so let's go to a little longer wavelengths. So 480M here is also a MIRI, nothing. And 770W, this is where we have the MIRI imaging start. A little bit, maybe I didn't notice at first, but then when I was looking at the 10 angstrom image, this extended emission just appears out of nowhere, and that's why when I looked back, I was like, maybe there is a little emission here. But then going forward to longer wavelengths, and this emissions start to get bigger and more prominent. 11.3 micron is there's a little less emission. That could be probably 2 reasons, because of probably the pH absorption feature, or the 11.3 micron filter, the F11 1130 wideband filter is extremely narrow. So based on that, you might not have gotten enough flux in there. So I'm not really sure why. But yeah, so it gets more and more pronounced. So you can see the flux is like increasing from IR to mid-IR. So just looking at morphologically, elliptical-ish in shape. So it has a diameter of major axis of about 8 arcsecond, which is 2 parsec at this distance of NGC 602, and 4 arcsecond, about 4 arcsecond semi-minor axis. Okay, so then I was like, okay, how does, let's check how the flux changes in different filters. If we go from outer, because this is still extended structure, so I want to see if it changes, if we go from outer boundaries to inner boundaries. So I just measure the flux in all the MIRI wavebands, and then in these contours. So this is the SK3 star. I kind of masked it out just visually, and then if I made these contours and then measure the flux in each contour for each band, and then normalize it to the 1500 micron, and then see the SED, and there's not much change going on. So it doesn't look like there's like different objects that are isolated, we can see. And then I overlaid with these black body models curves for a temperature of 120 Kelvin, 140, 170. So 140 kind of looks very close to it. So that concept gives an idea that it's a very cold object. So that's one thing. The first thing that we kind of decided. Then next, so it was like, okay, so what kind of object is that? It's very cold, close to this massive O3 star. So we started looking at all the scenarios. So first is background galaxy or AGN. A galaxy that size would have to be very huge if it appears in mid-IR. So we kind of decided it's not. Also, SED doesn't look like an AGN. Talked to people about, is it cold ISM or large dust grain? If that was the case, you would see some light scattering in optical or IR. So that's not the case either. Is it outflows from the O3 star? Again, you would have seen some sort of warm gas signature in near IR, and we don't see that either. Bow shocks, as Matthew was talking about the other day, and that's when I looked at it a little bit, but again, we don't have the signature arc sort of shape that we see in the bow shocks. So that's not either. So it looks like a YSO, because NGC 602 is full of a lot of young stellar objects. So we decided it is some sort of YSO. So what kind of YSOs? We'll look next. So we have the photometry for all the MIRI images for this object. So I took the the fluxes for that, and these are in this, the dot and the error bars, basically some 10% of the flux. These are the MIRI photometry. Then for NearCam, these are the triangulars. They are the upper limit. So NearCam is not visible, as I showed earlier, right? So what I did was just like took a empty region of the cluster center and set it as an upper limit of the flux, because if not visible, it has to be less than the background. And then perform the SED fitting for YSO models using the Robbie-Tail 2017 models. And then that kind of gives us a bunch of parameters. For that, we find this extinction is extremely highly extincted objects, a very dusty extinction of about 16.1. Based on the luminosity that we get from the model, the mass of this object is about 7.8 solar masses. So I compared that with isochrones to see if it matches with the ages of YSOs. So I looked at isochrone for 0.1 to 0.5 million year. I did want to mention that a class 0 and type YSOs are usually, they're very young. So usually their age is restricted to 0.5 million years. And that's why I kind of just looked at those. And this is where my object basically lies. And the mass from the isochrone is about 6 solar masses. But yeah, that kind of gives us an idea of it's very early stages of young stellar object. So to me, it looks like a duck, sounds like a duck, walks like a duck, so probably is a duck. So it's class 01 sort of duck, very cold, or class 01 sort of YSO, very cold, very early formation, and a little massive, and extremely dusty. Oh, already done. Okay, so and the other thing, so the MZS, because it's so extended, not very compact, we think it's a family of ISOs. There's not just a single object. The mass is being dominated by the most massive. The flux is dominated by the most massive object, which is about 6 to 8 solar masses. But then in the flux map, we look at 11.3, we have these multiple peaks, flux peaks. So these are probably the individual protostellar sources. Okay, so that was the interesting object MGS1 we found. The paper is about to be out soon, hopefully. And then the rest of the population, which is the bigger goal of this project, is the rest of the YSO population. So I was looking at the photometry is done, so I was looking at the color magnitude diagrams. This is the figure Peter has shown here earlier, and this is where he has found the brown dwarfs, all the brown dwarfs. This is the black line is the main sequence. This is the SMC field population. You have red club here, and then these are the isochrones for 1, 2, and 3 million. Sorry, 1, 2, 3 million years, and we have sort of found a candidate pre-mean sequence star population. And when I was looking at that, using that and then combined with MIRI filters, here I only showed 2, but there's multiple combinations and stuff. I made some cuts and then found these in here 350 versus 770. 770 is the MIRI filter. I found these candidate YSO population. Here at the very faint end of 356, these are probably contaminated by all the galaxies. I did try to remove as many galaxies as I could, other cuts, but so far this is the census, preliminary census that we have. And then just the spatial location, how they're a spatial distribution, how they're distributed. All the candidate PMS sources are here close to the cluster center, and then all the YSOs are at the edges of dust and gases. Sorry, yeah, and that's it. Comparatively, from Spitzer, we have 40 YSOs to about 400 YSOs. And there's my summary slide, and I'll leave you with that. Thank you so much.
2 minutes for questions. Okay, that's fine.
We only have 3 precursors.
Go ahead.
Have you checked to see if there's any ALMA data to see if you can your mystery object is like dust or CO?
Did you say ALMA data? Yes, there's actually a paper by O'Neill 2021. They have given a whole CO map of the NGC 602. So yeah, we have compared with that. For the YSOs, I still have to do that because it's in progress. But I looked at the distribution of that with the where MZS, that object or class 01 object that we have found, there is nothing there in the ALMA data. So, but we think it's probably because it was not as deep, the data. I have to look in more detail, but probably that's the case. Or it just is so cold that it's not traced by CEO. Probably like the dark molecular gas is not traced by the CEO. In that case, I have to check that more, but their paper, there is nothing there.
And then Josh.
Yeah, so similar to that, what about with ALMA, the 1.1 continuum? Because then to get down to the other part of the dust SED, like is it any 1.1 continuum data?
You mean like here?
Yes, yes. So because if with ALMA,
centimeters.
Yeah. I'm going the other way, so it'll be like what? 1,000. Yeah, so 1,000 micron ALMA continuum, like band 7.
Band 7, I don't remember if that it is there. I think it's 12 CL21 that they have published.
It's around there. That would be really good to really like constrain the mass if that.
That would be interesting. I'll check if that data is there, and otherwise we'll propose for that probably. What we find.
So I want to understand better. Actually, this is perfect diagram. So you have this. At 11 microns there.
Yeah, this.
And you had said maybe it's because it's narrow, but presumably you're giving this to us in scale units, where this isn't just the total amount of photons.
It is total flux.
So this isn't intensity units.
No, I mean I.
So the black body's an intensity unit, so I would have assumed that you know how wide the filter is.
I don't think they had scaled it to the other filters, so I'm not 100% sure what's happening.
Okay. My question is just, because we know the SMC is so deep, right, it's very possible to have distant structures that are bathed in a much dimmer radiation, and therefore cold. And so when you say it's right next to an O star, and then you say it's very cold, it seems very surprising.
Well, it's not right next to it. It looks like right next to, and it has to be in the cluster. Like it's so isolated, the NG602, and it has to be somewhere in the cluster, even because background, if it's a background object, it's a huge object.
Well, it could be 2 kiloparsecs behind.
Then
SMC is very deep. That's what they were interested in.
Just like that single object in outside the cluster in the isolation, that is also interesting. So yeah, we need spectroscopic information for that. All the answers, like so far, we think it's a class 01 object. All these answers where it's located, that is, we need spectroscopic observation.
Fascinating. Thank you so much.
Any other questions? Yes.
A very interesting talk. Amazing work. I was wondering if you thought about looking at this object in H2, any of the H2 lines, and seeing if that also shows up in these regions.
I'm sorry, can someone repeat it? H2 lines?
Yeah, H2.
Which H2 lines in the near?
I mean the H2, like 28 micron line, even that one.
Oh, molecular, yeah. So
near IR.
So same question actually someone has asked, like molecular lines. Again, H2 lines, I'm not sure they are. The CO12 to 1, I think that transition that people make the connection from CO to H2, that has been there, and they haven't found anything there. But
see if it comes up in H2.
Yeah, absolutely. Yeah, absolutely. Thank you.
Time for one last question if anyone has one. Otherwise, we should move on to the poster.
Thank you.
Okay, thank you very much for your talk. Leave you in the capable hands of Steve.
Thank you. It's our last flash talk session, guys. It's so sad. We just got here. Alrighty. So, all right. We're gonna start with Priya.
Hello everyone. So I'm Priya. I'm a professor in India in the university, Maulana Azad. And this work which I've been doing is basically with Gaia data. Somehow nobody spoke about Gaia. I mean, Gaia was not much mentioned. But the idea was basically to look for YSOs in Gaia. And the idea was that we use machine learning techniques So what I basically did is I took the C2D data. So we basically have also studied with another NGC 1333 and IC 348. These ones have also been observed with us by the Himalayan Chandra telescope. And what we basically did was that region has been studied by the C2D Spitzer survey. So we used that for the wire source. And using that, we made, this is our modus operandi. The wire source sample is from C2D data. We cross-matched it with Gaia DR3 data. We use that to get a control sample of the parameters for wire source in Gaia. And then we use machine learning techniques, BT scan optics and HDB scan to identify the wire source in that region. And then found other parameters. And then on the right, these are basically clustering techniques. You're looking for clustering in 5-dimensional space from Gaia data. And you can see the list of the clusters we found on it. And they are the region basically between IC348 and NGC 1333. Yeah, so they're listed over there. Do come and my poster is an e-poster, so you can have a look at it online. Thank you.
Thank you, Priya. All right, next we have Ronan. Take it away.
All right, thank you. So I'm looking at another nearby star-forming region. This one is Circinus, and this has a really interesting structure to it. So it's got an old population in the center and progressively younger populations going further out, similar to what we saw previously in this conference in Skosan. And it turns out that this is very closely replicated in both that and in the velocity gradient by these Starford simulations, where we see exactly the same patterns. And the way that these Starford simulations reproduce this pattern is actually by having what I call core-driven sequential star formation, is where you start star formation at the interface between the cloud and the cluster. And essentially, it works its way out as filaments that are left behind from residual gas sort of get eroded. And as the gas begins to be exposed to the central cluster, you get star formation moving progressively up these filaments. And we see evidence of this process happening or continuing in Circinus here, because we actually see the what appears to be a collision between the material ejected as part of this process and an adjoining cloud in the Circinus East molecular cloud. So if you have any interest in that, just come by my poster. It is right over there, number 6. Thank you.
Thank you, Ronan. And lastly, we have Kieran.
Okay, hi everyone. My name's Kieran Rogers. I'm a final year PhD student at Leiden University, and at the end of the year, I will be starting a position right here at Space Telescope as an ESA fellow. Most of the stars and planets in the Milky Way formed in clusters, bathed in UV radiation from massive stars surrounded by high densities of interstellar gas and dust. These kind of environmental factors can facilitate processes like external photoevaporation and late-stage accretion onto the protoplanetary disk. The vast majority of detailed observations of protoplanetary disks has been done for low-mass star-forming regions nearby, where these environmental factors are weak or entirely absent. We measure the accretion rates of 42 pre-main sequence stars in the Milky Way starburst cluster NGC 3603. We found that their accretion rates were systematically higher compared to similar stars in low-mass star-forming regions. Some of the stars in our sample were in excess of the general trend that we found for our own sample, and we found that stars in this sample that are associated with high densities of molecular hydrogen in the interstellar medium show enhanced mass accretion rates above what can be explained by their age and mass alone, hinting at an environmental relationship between accretion and the ambient gas density, possibly a signpost of late-stage accretion. Thank you.
All right, anything from our chairs? That's our break then. We'll be back here at 11 in a half an hour.
Left on the.
Pardon me. Dropping F-bombs this early in the game. It's too soon, man. Oh yeah, don't. It's not gonna automatically.
Works?
Yes.
Yes?
Yes,
Okay,
sir.
great.
If I spaz out with this thing,
Are you,
this works, right? Yeah.
When you're ready,
I'm a
we'll keep
huge
throwing them on.
spaz. So. Oh, screw this up.
There's a button right on the top right there.
Should we turn it on? Not yet.
Maybe we should if you're ready. Ready? All right, let's do it. Here. Here we go. It is live. All right. Welcome back. It's right 11 now. Okay. Let's see. Okay, thanks for coming for YSO's Part 2. Very exciting. Okay. That was not supposed to be sarcastic.
Okay.
I'm sure we all are. Our first speaker is Amy Stutz about cluster formation in Orion and the Gould.
And beyond.
And beyond.
Beyond. We're getting out of the Gould Belt.
All right. I trust you.
We're going to try to get out of the Gould Belt, except for Orion. All right. Everybody hear me okay? Great. So it could be louder. I'll try to be louder. I'm not very good at being loud. But anyway, timescales. Is it on?
Green light.
Yes, the green light. Everybody hear me? Okay. So we had this very interesting discussion that I think Tim led on timescales, right? And so one of the main issues here is this disconnect in timescales in terms of star formation tracers. This is an old story. We all know it. I feel like we don't exactly know what to do about it. And part of the reason why this conference has been so cool is that we're trying to get at what we're going to be doing about this. Now, this talk is existing in this kind of regime, and there's a reason for that. I want to get at the physics of star formation that's happening right now, not just some past averaged thing that's maybe harder to interpret. And so for that, we really have to go to these younger objects, these things that I apologize for the jargon. When I say disks in this talk, what I mean is young stellar objects, young stars with disks of order 2 million years of age, half-life approximately. Protostars are 500,000 years, class 0 maybe 0.3, and so on, okay? And we can start to add a few more objects to this list, and this one comes with a question mark because we all know that once we see the word core, we have to be asking ourselves, what is a core? And some of them are better defined and some of them less well defined. I'm not going to get into the details of cores, but I will mention them in the framework of some kinematic analysis that we've been doing. And in that framework, I also will present some kinematic features that we've identified that are associated with cores that we hope we can, in time, as we deepen the analysis, use as indicators of very early star formation from a kinematics point of view. And so we want to use all these telescopes and facilities, all these machines, to get at the star formation problem. I already told you which regime of timescales this talk exists in, so this is causing an additional pressure on the problem where we need very high resolution. So we need the wavelength access to get at the cold objects, and we need the resolution. And that is going to force us to get into Milky Way systems, right? Now, ideally, we're talking about Milky Way systems. If we want to talk with each other, we want to talk about things that might plausibly at least be detected in extragalactic systems, right? Not Taurus, which anonymous people in this audience have called irrelevant fluff. We want to get at things that are a little bit, you know, that are cooking a little more, right? And so that's what I'm going to try to do by talking about Orion. So this is a mass map of Orion from Herschel, and it contains about 10 to the 5 solar masses. So plausibly detected in extragalactic systems, and the ALMA EMF survey, okay? So this is a survey of protoclusters, and I'm gonna start with ALMA EMF. I'm gonna be super brief, huge amount of people, great team, lots of work, main science driver, which I'm not gonna talk about, but Maxime will in a couple talks, is the temporal, to constrain the temporal emergence of the initial mass function from these gas-dominated protoclusters. These are sort of garden variety Milky Way protoclusters with a uniform, I would say, or approximately uniform selection function that's already rare in star formation, especially in our galaxy. And they're selected from ATLAS-Gal. And the range and distances for these objects is about 2 to 5 kpc, but they're observed with ALMA at matched physical resolution and at matched sensitivity. So, you know, ALMA is our Fourier machine, and we can tune it to whatever resolution we want. We take advantage of that so that we can at least plausibly argue that we are able to compare apples to apples in the ALMA EMF survey in aggregate, okay? Now, we have our alphabet soup of ALMA lines. I look at this, I'm not a chemist, it's a headache. And so I'm only gonna talk about diazonelium today, N2H+. For those of you that know ammonia, diazonelium is very similar in critical densities and temperatures that it's tracing. And we're gonna talk about two particular, actually 3 protoclusters in this tracer. But with ALMA EMF, we're doing all kinds of work. And in a little bit, you can hear about much more of this from Maxime in his talk, okay? So why so inefficient? This should be a familiar question, at least for me. Just in terms of my personal approach to work, but generally, when we look at G351, we see this really massive filament. It's got cluster formation on one end, and it's very inefficient compared to local relations, which is this part of Rob's work. Rob couldn't be here today, had to leave early. But anyway, you know, we have these local relations. These are like 12 nearby clouds out to like 1.2 kpc, and they have pretty uniform efficiency per free fall time. And this G351, even when completeness corrected, is falling below. And we want to ask, you know, what's happening here? And this is even considering the fact that it's got this protocluster that's part of ALMA EMF. So we're going to start by looking at the protocluster. Ultimately, we're not going to be able to answer this question today in this talk. We're still analyzing the data, but we do want to get into the kinematics of the protocluster. And so for that, we're going to turn to Nico's work, which is now published, and we're going to look at N2H+ and these complicated PV diagrams. And to first order, what we see is that the PV diagram in the dense gas is consistent with gravitational contraction. That's good because we're forming a protocluster. If it wasn't, we'd be in trouble. And then we see a bunch of small scale features that gave us many headaches. But we think we can say something useful about these features. So here's an individual, one of these features that we call V-shapes very creatively. And this is the position of the core. And so we think these are inflowing gas that are feeding cores. If we think about cores as small n or individual massive stars that are forming in the sample, we know we have to feed them with mass. And from these PV diagrams, these are just phase-space diagrams, we can get time scales. And by fitting the N2H+ line, we can also get mass estimates, and so with time scales and masses, mass accretion rates, et cetera. And so on average, these PV shapes have about 30 kiloyear time scales, so they're pretty short-lived, but they're longer than the free fall time. They're about a factor of 3 the free fall time of the core itself. So they're gonna be feeding these cores for a while. And one of the implications of this is that if we add up all these little V-shapes, this diagram isn't showing up great here, but anyway, trust me, there's V-shapes in there. We would consume the mass in the cluster on a very short time scale. So this requires additional feeding if we want this thing to grow for longer. Now, fortunately, I already told you that we have this massive inefficient filament. This mother filament we think is feeding the protocluster, and we're going to be testing that in the short term with new ALMA data that we're already reducing. So yeah, we think these might be viable early star formation rate indicators, and we detect the V-shapes that aren't associated with cores as well. So we think those cores are just below the continuum completeness limit in the ALMA data. In a second, and oh yeah, I forgot to mention, these results actually are not just G351, they're also in G353. So my attitude is probably incorrect, but the first order is you see it in one region, it could be a curiosity. You see it in 2 regions, it's generic. So we'll see if that pans out. In G12, we also see some V-shapes, but it's not the main focus of the analysis. What we have in G12 are 2 prominent filaments that are sort of feeding into the center of the protocluster. And what we find is that in R1, on average, if we collapse the PV diagram and just look at the aggregate gradient perpendicular to the ridgeline, the long axis of the filament, yeah, we see this gradient, which we interpret with a rotation model. You don't have to buy into that, but anyway, the velocities in this thing are spread out, whereas in R2, they're very concentrated. Now, R2 has a bunch of cores, outflows, SIO, you name it. It's getting on with this business, star formation, and this guy doesn't know what it's doing. It's not really doing anything. So we want to link the physics of the collapse to the star formation efficiencies and star formation rates. And that's why we argue that this thing has not yet shed its angular momentum to achieve this more concentrated phase of star formation in this filament. And so what's missing from this picture, I thought I'd be really subtle, but we would like to get some of this data so we can play some interesting games with YSOs. And I don't know if you guys know the saying, but my grandfather used to say it. I can't say the whole thing because it's not appropriate, but you say you can want in one hand and something else in the other. So it's better, we can say we want this, but it's good to show some examples of the kind of games that we would try to play if we had these YSO distributions in these typical Milky Way protoclusters, right? And so for that, I want to turn to Orion. Now this talk contains 0 JWST data, but we can play similar games that we've played in the past from things like Spitzer, right? And so what do we see in Orion? So this is Orion A, right? And this is the ONC. Everybody's sick of hearing about the ONC. But we want to ask in the cloud as a whole, so the background image is Herschel. It's a column density map, so this is a model, right? But it's cold gas, and I just think of this as the cold gas map of Orion A, right? And at the top, we have this squiggly thing, it's integral shaped filament. The black line is the ridge line. It just traces the column density maximum through the image. And so it's the bottom of the gravitational potential. And so the first thing we ask is, where are the protostars? Spitzer identified protostars, right? And they're on the ridge line. It's like beads on a string, more or less, but especially in the integral shaped filament. And where are the stars? Here, stars are YSOs. They're young, half-life 2 million years. They have disks. Spitzer identified. They're spread out. And so how do we get on a 500,000 year timescale type objects to separate them out from the bottom of the gravitational potential? That was sort of the main question. And we thought it was pretty puzzling. So, you know, we just proceed. And, you know, Orion is complicated. I don't think it's any more complicated than any other star formation region, but we're going to separate the components out into simple geometry. So cylindrical cow, spherical cow. ISF gas filament will be modeled with a cylinder. It has a power law density profile, okay? And we're going to model the stellar component with a sphere. Neither one of the two follow these, but you know, we got to simplify, so fine. So here's a zoom in on the ISF with its little ridge line. It's not perfect, it's got a kink in it here, etc. We're going to focus on the center of the ONC, and we're going to extract line mass profiles in there. Also for the stars. So you can see the star mass distribution, they're spread out all over, but if you go close enough to the center, spherical isn't too bad. And so we get some mass profiles. Here's the power law of the gas, and this kinked thing for the stars. Now it turns out that, I already told you, this is a good power law fit, that's fine for the cumulative mass per unit length. For the stars, it turns out this is fit reasonably well by a plumber. Plumbers are good because they have beautiful math, potential density pairs and all this, super easy, even for people like me. So we can get densities. We have an inner softening radius for the stellar distribution of about 0.36 parsecs. And things get interesting when we look at the gravitational field. So the gravitational field is gas dominated everywhere except at the inner softening radius of the Plummer sphere. So this gave us an idea that perhaps the filament, which is not, I don't think it's a crazy idea because this filament has a lot of mass in it, is setting the structure of the stellar cluster at early times. It also implies that we can't consider the stellar cluster alone as virialized. Right? So we want to ask what are the kinematics anyway in this system? Because if we're talking about, gravitational potentials and things getting separated from filaments, are things really moving faster? What's happening? So we used ammonia to trace the protostars, which are in yellow, a low resolution CO map to get at the cloud velocities. And in blue, we plot the apogee near infrared radial velocities of the disk stars, okay? And we can see that, in fact, oh yeah, so the red line is the ridge line, but in velocity space, right? So we can see that the protostars are pretty clustered near the red line, and the blue points are spread out, the disk stars. So not only are the disk stars separated from the filament in position, but they also have faster velocities compared to the protostars. And so we can say a few things by collapsing these diagrams. First of all, the whole thing, stars, protostars, all of that is bound because we measured the potential, right, from the gas and the stars. Second of all, the timescales in the ISF are short, about 0.4 million years. And so we can also ask ourselves, what do the phase space diagrams of these populations look like? And so the axis ratio of these position velocity diagrams is set to 1 million years. That would be the diagonal line, right? So steeper structures than that are shorter time scales, and more spread out structures are a little longer. And we can also see that the system isn't completely mixed, so the color coding is the position and declination. I should also note that these diagrams have taken out the wiggle of the filament, both in position and in velocity, right? So these are relative to what the gas is doing. And that's why they don't show these extra wiggles that we've been seeing. But anyway, we can see that the stars aren't totally mixed. Here they're dominated by this greenish color because in the center of the LNC is where we have the most sources, right? So our idea is that maybe this filament, again, it's like I think it was the previous talk, right? The duck theory. If it looks like a duck and it quacks like a duck, maybe it's a duck. Maybe this thing is a wave. So you have to take this thing with like a Mount Everest sized grain of salt. This is based on Gaia data and it needs to be updated. But anyway, we took the YSOs in a thin strip following the positional ridge line of the filament and average the parallaxes along the filament. And what we find, so from your point of view, is that it looks like the average parallaxes go towards you, then away from you, and then back towards you. That's what these red points show. And then things got a little funky because we're like, well, let's plot in green and in gray the CO in gray, and in green the diazonelium. And see how they look. And this looks like the velocities and the positions are correlated. So do you guys know what kind of wave would give rise to this to the positions and the velocities being correlated? Do you remember? No? It would be something like a standing wave. But we remember from like 3 seconds ago that the filament on the sky also has the shape of an S. So it cannot be a correct model, but maybe if we combine this S impression and this S impression, we come up with a model like a corkscrew, or something like that. Again, grain of salt, boulder of salt, whatever. But it's plausible that this thing is actually moving, stirring the potential, and helping to inflate the velocities of the stars. I would also like to note that we took remedial, but some measures to try to take out the velocity puffiness from binaries. Okay, so we don't think it's binaries, just inflating the velocity field, right? So this led to basically a cartoon where we thought, okay, the protostars are mostly gas, they're envelope dominated, they're stuck to the filament, right? And then the filament's moving and the protostars are collapsing, and at some point, they just become too compact, the filament can't hold on to them anymore, and they just leave, according to Newton's first law. And so it's the gas that would be accelerating away from the disk stars, rather than the other way around, and that's how we could get this heating in this filament. And so we can try to go back in time. We don't have the simulations that we saw, for example, yesterday, but we can ask, what is, the ghost of Christmas yet to be look like in our INA, for example. And we can look to the north, and we see there's a couple clusters, and they have an age gradient. So it gives the impression of these repeated sequential bursts of star formation, where what we see today in the ONC is just a full-blown, still gas-dominated protocluster formation. And if we ask Christmas past, what do we see? We might guess that this thing is propagating down, and so Christmas past of these guys up here would be something like the bottom of the cloud, which is still very massive, but hasn't yet collapsed into this sort of full-blown cluster formation phase. So that's kind of the idea. And then the last thing that I have to deal with, or we have to deal with, but I'm not dealing with in this talk, is where could the weirdness in this filament be coming from? And we put forward that maybe it's the magnetic field. Now, I don't work yet on magnetic fields, but we did some simple calculations. It seems to pass muster, but more work is needed there to get at the bottom, to the bottom of this. So the take-home point is that stars are forming on filaments, but forming clusters, and we should, as best we can, consider the dynamics of the gas, B fields, protostars, and stars together to get at how we're forming protoclusters. Thank you for listening.
Plenty of time for questions.
I'm wondering, in your oscillation model, do you have a sense of when the filament stops forming stars and clusters and stops making a puffier system because of the oscillations? Is it just when it runs out of gas, or?
Yeah, so I think I don't have a great answer, but from looking at the clusters in the north, there's no gas and they're still pretty young. So I think the gas is mainly getting consumed into those. And that's when it would, quote, stop. But the other side of this is that if this thing is oscillating, the ONC isn't centered on the filament, right? And so maybe the cluster is also as a whole getting ejected.
Oh, I see.
So, once you start inducing these relative motions, things can happen.
Yeah, sure.
I don't know that much about YSOs, but what is the approximate age range of the things? Like you said that they were sequentially forming, but like what's the time period over which they have done that?
So I didn't say because I don't know. But it's an age gradient in the sense that the disk fractions are varying. And I'll try to get at an age for you, but I would have to look at papers that are not mine, that are on about these objects. But we looked at the disk fractions and we're like, it's game over. age gradient.
I love this 3D velocity stuff. It's like my favorite thing in the world. So I was thinking about your V, what do you call them?
V-shapes.
V-shaped objects. And I was thinking you're showing at the bottom right of that image that you had the on the near side was sort of a kink where the star is, and you have these two sort of inflowing things.
Yes.
And I was wondering if you rotate that so that the observer is from the bottom, you know, think about it that way, or that should happen sometimes, right? And that would give you kind of an appearance in the velocity space of like a V this way, where the protostar is at the top. Do you ever see that, or am I getting it wrong?
I don't know if we see that, but what we did do is lay down, because we have cubes, we can lay down slits at any orientation and see if the structure is recovered, and it is. So we think this is robust. Now, the PV diagram, it collapsed in the other direction, does look quite different. So there is a geometric, so this is really a cropped figure where we have the other PV diagram in this way, and things do change. And in this one, I didn't mention, I should have, for example, we see a rotation signature. So we also think that these clusters are globally gravitationally contracting, but still have some spin inside. So that's outside in evolution. This isn't getting at your question, but anyway, there's more info in here. And personally, if I'm honest, I'm not totally satisfied with this model, but it seems to pass muster. We see a couple ideal cases where the outflows are going perpendicular in space, so this isn't outflowing material. And the velocity scale is very different of the inflow versus the outflow. Outflow is much more energetic. But anyway, we need to have better models for this. But we also had to stop and say, let's publish a paper for these poor PhD students.
Was when you did the N2H plus, how did you fit that velocity? Because normally, like, you get like multiple components along the line of sight. So I was just wondering, are you just using the strongest component, or did you just fit one?
No, we do the full hyperfine fitting of all 7.
Like, not just the hyperfine, I mean like multiple components along the line.
We do the full hyperfine fitting with 2 velocity components, and we stop there. And that's why you only see 2 colors in this diagram.
Okay.
There's a few places where we feel like it could be justified to do 3, but you'll have to take some LSD to interpret it, and it's so small that we stopped at 2.
Okay.
But we're gonna have to deal with 3 components. We started, and it's a lot of LSD.
It is a pain.
Yeah.
So first, I want to thank you for saying diazonillium is my favorite molecule name. People always say N2H+, so just thank you for bringing some more joy to my life. The second thing is, I was mentioning about seeing these V-shaped things with no detected core yet at the tip. So you basically have like an as yet undetectable core, therefore probably below quite a low mass threshold, but a lot of mass you think is going to flow into it. So are these like places where you can say like ahead of the core really forming that the core mass has already basically been decided by the cloud structure, and you can say what that mass is going to be ahead of time?
We did not think of that kind of deterministic argument. I was a little more simple-minded and just thought, the continuum on my MF images just missed some stuff. And we have booming lines in a lot of areas. But that is a very cool idea. You can work with us on our next paper.
Okay. You referred to Gould's belts, and I know that there's Gould belt survey was really important, in this field, especially in the Herschel era and so forth.
I wasn't in the Gould belt survey.
Okay, well, I know people talk about it a lot. Those of us who work in 3D ISM don't think it exists. Do people we don't think it's belts? Do people in this a circle still? Or like Gould suspenders?
I think people think it's a circle and they get really mad. And I kind of don't like them too much.
Okay. I'm just curious whether these two communities disagree on this or whether it's just kind of like nomenclature or what.
I mean, I think if you want to change that paradigm, you talk to the young people. And that's what's happening.
The chairs are taking over. Sorry, guys. It's awesome. I have a question about this similar V-shaped structure, referring back specifically to Laura's talk, where we see similar structures in the Magellanic Clouds, where we have these 2 filaments coming in, one coming in one direction, one coming in another direction. the idea is that they collide, and then there's a massive protostar right at the collision point. So my question is, one, is it a similar structure? And two, is the collision needed, or is what we're seeing in the Magellanic Clouds just gas flows?
You can argue that there's a series of filaments coming together here. This arrow indicates the direction to the main mother filament. This is why I asked, if I'm thinking of the same talk, if they looked at the velocities and not just the line widths. So I can't answer the question about what's happening in those filaments without seeing something like this or a moment one map or something like that. But I think it's incredibly rich what could be done. Is the collision necessary? There's a lot of hub filament systems that are being observed. Some people call that G12, the other one with R1 and R2 that I showed, like a hub filament system, and you could see why, you know? Yeah, I think if you want to form massive stars, you got to collect a lot of material. So some kind of concentration mechanism should be necessary. But I don't know that it needs to be specifically some hub filament system thing. That's kind of like a popular jargon right now, but you know.
I have two very short but self-serving questions. Are there any measurements of the magnetic field strength in this region?
In the ALMA EMF?
In the part that
Yes, there are. Hylas, right? He had a series of papers where the first one, I don't even know if it was the first one. The first one I remember, they got, and Josh, you'll know better, was it OH or anyway, the semi-diffuse gas around Orion A. So not getting into the heart of the, yeah. And they came out with the idea that it was because you sample with Zeeman, you get the line of sight direction. So they saw a flip. And they said, oh, clouds could have helical fields. Yeah. And that was super cool. But then he wrote another paper. He said, no, strike that, not helical. I'm on the helical. But anyway, you can get some magnetic field strengths from those measurements, but they're sparse. And we picked a couple and tried to see if the magnetic energy density matched the potential, blah, 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 to see if there's free energy in the system that would allow for wiggles. If we're going to claim this thing is bound, you know, you have to have something changing on the scale of the wiggle. And it seemed to hold together, but it's not satisfactory. And then on the actual filament itself, from some millimeter dust polarization, the magnetic field, where you don't get strengths, no matter what anyone tells you, you can estimate strengths. But anyway, you get the projected field direction, and the field is perpendicular. So we just said, we are simple-minded people, and we have this direction here, that direction there. It's a circle. That's what we got.
We're pretty much out of time, but I did see one more.
I'm going to ask my question.
Okay.
Yeah, that's
so let's
thank you very much. All right, our next speaker is
Yep.
We'll talk to you about SAG B2.
Hi, everyone. My name is Nazar Budayev. I'm a graduate student at University of Florida, and let's jump straight in. So I hope you don't need convincing that star formation processes, at least on some level, are interconnected. And I want to use this time to use Sagittarius B2 as an example to show you how these processes interact between each other and with the surrounding ISM. So we had great introductory talks to the CMZ, Central Molecular Zone, on Thursday. But just to make the point clear, everything we know about star formation in the solar neighborhood is not really applicable to the more extreme environments of peak star forming period at around redshift of 2. And we can compare the environment in the CMZ and the solar neighborhood, and we can see that, well, it's way more extreme. And maybe it's not exactly representative of the environment where most stars were formed. We can still use it to kind of gain more insight into formation of stars in the extreme environments. We can also keep in the of our mind, coming back to Rebecca's talk from Thursday, objects like NGC 253 and star formation there in the extreme environment. I mean, again, maybe not exactly representative, but we can use central molecular zone as a stepping stone to interpret the information we gain from these objects here. And the interesting part of this about CMZ is that we can resolve individual star-forming objects. And I introduced to you Sagittarius B2 molecular cloud. Despite being less than 1% in volume of the whole CMZ, it contains 10% of the mass and about 50% of star formation. So again, it's a great laboratory to look for those forming stars in an extreme environment. And before we proceed, let's just set up the picture in our mind. We have what processes and objects we can find in the forming molecular cloud. Well, we'll have some dusty YSOs embedded in a lot of dust. If there is accretion happening, there'll be outflows. If you have massive stars, you'll get H2 regions. Eventually, some of the dusty YSOs will accrete the material around them, revealing the central stars. And if the conditions are just right, you'll also see maser emission, which I think was only mentioned like a couple times during this conference. All right, so we are looking for stars in Sagittarius B2. Well, let's observe the cloud with ALMA at 3 millimeter and 1 millimeter to find the earliest dusty YSOs. And, well, we find a bunch. In fact, they're distributed throughout the cloud. We find over 400 of them. They're compact and dusty sources, about 1,000 AU in size, rotationally supported, and about 50 Kelvin in temperature. Now we can rule out some other possibilities in very rudimentary analysis, like could they be pre-stellar cores? Not really, because of the short freefall time. Could they be stage 2 YSOs? Again, not really, because there's just so much dust that we are seeing. And could they be H2 regions? Well, technically, yes, but they would have to reside in a quite narrow parameter space. But remember that. Remember that part. All right, so we're looking for stars. Another option is to look for H2 regions, massive stars. And again, we observed the cloud with VLA, and in Meng 2022, we find a bunch of 50 tiny H2 regions that are surrounded by this dense gas, foreshadowing. Let's move on to slightly to the south, to a younger part of the cloud, Sagittarius B2 deep south. And I want to highlight work of an undergraduate student at the University of Florida who cataloged another 350 YSOs in this region, bringing the total count to almost 1,000. And having access to ALMA continuum, we also get lines such as SIO, where we find a bunch of outflows with these high resolution observations. And I'm just showing you a couple examples, but the point is there are a bunch of SIOs. Great, as expected, stars are forming there. All right, again, we are looking for stars. This time we use water masers that trace massive star formation. We observe the cloud with VLA, we find a bunch of masers, 500 of them, great. So what? Well, now we have all these high resolution observations of protostellar cores, H2 regions, outflows, and we can put them together to construct a better view of what our objects are. Whereas if we only looked with VLA and saw masers kind of in this configuration, probably this looks like an outflow, but now we can tell for sure what these objects are and what the nature of this maser emission is. And we can classify these sites of maser emission based on the nature of the sources, and we find over 140 sites of water maser emission in Sagittarius B2 cloud. And I want to highlight this because this is more than a factor of 10 sites of water maser emission in one environment, in one cloud, which means that now for the first time we can use the statistical data about these different populations of water masers as interpretation for surveys. Let's move to one of the protoclusters, Sagittarius B2, and it's forming stars, some H regions, but in Sgr A 2019, they observed the region and they found these filaments. They're bringing in material for the cluster, feeding this central cluster. Now we can zoom in with the high resolution ALMA data. We still see these filaments in the continuum that are bringing the material. Great. But also, we have high-resolution observations of SIO. And we see this outflow. And, well, we knew that there's an outflow happening over there. But now, with these high-resolution observations, we can see how it interacts with the inflow seen in the continuum. And you can say, oh, well, maybe it's projection effects that you just like ended up being lined up exactly. Maybe it's optical depth effects. Well, we can go back to our maser data, which traces shocked emission, shocked gas, and see that indeed this outflow is smashing into the inflowing material, mixing, and which means that we are resolving feedback in the densest region in the local universe. Now, in addition to that, if you kind of draw a line through this outflow, you see that, again, with high-resolution observations, there's basically one object in the continuum here. And just to be clear, it's about 500 AU in size. So we interpreted this as it is just one central object that is shaping the protocluster instead of combination of stars that are being shaped by an inflowing material and the producing outflow, shaping the resulting outflow. All right, we looked for stars. Let's keep looking for more stars. This time, we want to find evolved YSOs, and JWST is the instrument to do so. And since we are on this slide, oh, by the way, I turned the image 90 degrees just to so you can see it a little bit better. But since we're on this slide, I want to mention a couple of data reduction struggles that we had along the way, such as background contamination and crowding. For example, in this field of view, we have over 100,000 sources in all 11 NIRCam filters matched together. So if you have dealt with these issues, I'll be happy to chat with you about it. And just to drive the point home, this is W51, the cloud slightly out of the galactic plane. This is the brick. I don't know how well you can see on the slide. Another cloud in the galactic center, and just the sheer number of stars in Sagittarius B2 that we have to deal with. So all right, we look for YSOs, evolved YSOs. We find these kind of objects that look like YSOs. We fit YSO ACD model. So is it another duck? Well, remember this slide? Remember we talked about H regions. If we fit a basic model of an extincted H region, it also kind of fits the data. So what's going on? Okay, well, let's go and look for VLA and ALMA stuff. Did we miss them? And well, we're just not sensitive enough. They're just so small. Not only that, because these H regions are surrounded by dense material, they become optically thick in VLA frequency, meaning we need even higher sensitivities to detect them. And in red, I'm showing the best case scenario that we have in the cloud that covers a little bit of the cloud. Still, it's not enough to find these H regions. So we propose for ALMA band 1 observations that will hopefully detect this hidden population of tiny, tiny H regions in Sag B2. Now, one more slide here, which is, you might have noticed earlier that these ALMA YSOs are kind of distributed on one side of the cloud. And you can draw basically a straight line through. There is nothing happening on the other side in terms of dusty YSOs. So what's going on? Well, we don't know. And we had a lot of interesting talks this week. Maybe it's bubbles. I don't know. You tell me. I'll be very interested to learn what you think about this. Now, another thing we find is that there is no overlap between ALMA YSOs and JWST sources, all the way to 25 micron. So just to make it clear, all the talks that you've heard today, just put a bunch more dust in front of all the objects to the point where you can't see any of the ALMA YSOs with JWST. There's just so much extinction. But yeah, so we find this asymmetry, and the ultimate goal here is to use JWST to find this later evolved population of YSOs and compare their spatial distribution with the dusty ones and see, do they follow kind of how it is in Orion? Are they more distributed? Will we find them on the other side of the cloud, whereas the younger star formation is happening here a little bit lower? Or are they exactly the same? So we can gain insights on how this cloud formed and its star formation history. So with this, I'll leave you with the slide with beautiful data in the background, and I'll be happy to take your questions.
Any time for questions?
You mentioned the lack of correspondence between the ALMA YSOs and the JWST sources.
Mm-hmm.
I mean, could that be remedied with deeper JWST observations? I mean, is it feasible to recover those sources?
Remedied, you mean? Well, we don't see them because of just the high extinction. So,
is it just? I mean, if you go fainter and fainter and fainter, could you pick up some of them?
I don't think so. With NIRI, I think we're reaching basically the limit of the sensitivity we can get. Yeah.
Correct. So the image where it's on the same topic, you showed a bracket alpha image. How are you identifying YSOs with JWST? Is it based on bracket alpha emission or near-infrared excess?
Well, we would have hoped it would be easier, but the idea is indeed to use accretion tracers, bracket alpha emission, to use color magnitude diagrams, just try to extract some information from there, but we are still working on data reduction there. It's just there's so many objects and there's so much extinction that it's really hard to tell what are really YSOs, what are embedded stars, what are red giants, etc.
Related question, what do you mean by involved YSO?
Yeah, well, the stage 2 and 3, let's put it that way. And yeah, I've been using stages. You've heard classes earlier, but the idea is that the dust has been kind of removed and it's past the point where we can detect them with ALMA.
Liz and then Bob.
So I see that one of your ALMA YSO sources overlaps with something that looks like it's their JWST. Is that just an intervening?
Is it here?
Bottom actually.
Here.
Here.
I think, unfortunately, this is just what is it called? Saturated pixels that are shown in blue here. Oops, my bad.
Oh.
But yeah.
Sorry.
But yeah, this is just a foreground, very bright star.
Yeah, gotcha. Never mind.
Yeah, so my question is addressed to you, but anyone who knows about YSOs, it would be helpful. I'm the co-chair of the Roman Galactic Plane Survey Definition Committee. And one question we are debating is the question of we're going to recommend covering the galactic plane with the equivalent of the JHK filters, going very deep, so about 22nd magnitude. But we're sort of still split or undecided on whether it's better to use the 1 micron 106 filter or the 1.84 micron filter that contains Paschen alpha. And so the question is, if you could go deep in one of those two filters, which filter would you pick for YSO science and why? and I don't mean to put you on the spot, but if you have thoughts or if anyone has thoughts, please talk to me after the meeting.
I will say, well, I'm a little bit biased because of the JWST data that we have. We also have Paschen alpha filter, and it is very extincted. A lot of emission just gets extincted, so we barely can pick it up with JWST. So it would be great to have high sensitivity observations with Paschen alpha, but I'm also interested to hear what everyone else thinks.
Yeah, I can add on this. I think emission lines are by far the best way to detect disks. There's a very recent paper that came out using Gaia to look for accreting stars. There are tons of stars accreting that show no detectable near-infrared excess. It's a coarse way of finding YSOs is near-infrared excess. Emission lines are a much more sensitive way. In very high extinction environments, you'll suffer with Paschen alpha simply because it's around 2 micron. So maybe there's an argument in a really extreme case, but I think overall emission lines are really the better way to search for disks.
Also, 106 sounds pretty short.
Yes, it's short. So obviously, maybe in these kinds of environments where it's super high extinction, it's not the best choice to do 106. But maybe for other YSOs and other environments. So anyway, I just wanted to raise this issue, and please feel free to talk to me after the session because we're mostly leaning towards 184, but there is some people that still think the 106 is better for their science cases. So.
Time for one more question if anyone has.
Oh, that's okay. So I'm just curious, like, do you have any thoughts about the star formation asymmetry? I mean, I have, I'm like racking my brain, I can't think of anything. So do you have hypotheses?
Well, I've heard a lot about bubbles this week. I started pushing that interpretation into my brain. I don't know, maybe is this an expanding bubble? But other than that, not really.
We should look for it in the simulations.
One more call.
Oh, I don't know if it's a bubble either, but like, could it be like along the line of sight that you have that, so the way the inclination is, and so behind it, it's extincted? Like, that's the only thing I can think of, because you start to see some come back up around there. So either, I don't know, that's the only interpretation I have, is potentially just the line of sight. I don't know if that actually makes sense or not. That's just my naive first past post opinion.
I'll also say on that, and again, this is all up to interpretation. We don't have exactly an answer yet at all, but we can see these expanded.
It could be in the front.
Yeah, these expanded H regions can be in the front indeed, but maybe there's just the material is less dense here. So we don't see any of these extended H regions, maybe because they're being pressurized by the surrounding environment. So maybe high resolution dust maps of the region would be helpful.
All right, let's thank our speaker again. And our final speaker of the conference is Maxime Valleil-Manet.
Yeah, it's all right. It's all right.
Close it up. I can do it.
Okay, so everybody hear me well? So hello everyone. So first I would like to thank the organizers for giving me the opportunity to talk today and even to close the symposium. So my name is Maxime. I'm currently a first-year postdoctoral fellow in Grenoble in France, working with Frédéric Motte and Fabien Louvet. And so today I will present some results of the ALMA MF survey, so top heavy CMFs, protostellar outflows and high mass prestellar cores. So before digging into the CMFs, we first need to talk about the IMF and its universality. So the IMF, or initial mass function, is the mass distributions of stars at birth, and it has long been considered in the past studies universal, okay, and modeled by a series of broken power laws, with the very well-known salpeter power law towards the high mass end of the IMF, or by a log normal function plus a power law. But in the end, maybe the IMF is not so universal, okay? So if you want to investigate the origin of the IMF, if you consider that the cores are the star's progenitors, then the mass distribution of cores should be the progenitors of the IMF. And so the surveys of the past 2 decades, they suggested a direct link between the IMF and the CMF, which is the fragmentations of molecular clouds into cores could determine the stellar masses by assuming a core-to-star efficiency and very simple assumptions. So in the end, the CMF is really a good metric to investigate the effect of the star formation environment on the star formation process. But all these past studies, okay, they were only done in low mass star forming regions, so this is not really representative of the main mode of the star formation in the galactic disk. So that's where ALMA MF enters the room. So Amy talked about it a bit. So the PI Frédéric Motte. So it's an ALMA large program that mapped 15 massive protoclusters between 2 and 6 kiloparsecs, basically. And they are really more representative of the Milky Way star-forming clouds. So we have various evolutionary stages of protoclusters, and we have access to a strong and a huge statistical basis, of course, to study this link between the cores and the stars. So here you have a bunch of the presentation of the ALMA MF survey and the dataset papers. And so, as I said, the protoclusters are at several evolutionary stages. So when you look at the free emission in these protoclusters in function of the ratio between the 1 millimeter and the 3 millimeter flux, as you go towards further to larger ratios, the free emission slows. And so basically you have 3 evolutionary stages. So you have evolved regions here with extended H2 regions, intermediate regions with ultra-compact H2 regions only, and then young regions where only thermal dust filaments dominate. So in young and intermediate regions, you have a mix, you are dominated, by the thermal dust filaments, while in the evolved regions of ALMA MF, there is clearly a mix between the thermal dust emission and the H2 regions. So now that I have presented the protoclusters, we can dig in the CMF of these protoclusters. And one of the first results here, led by Johan Puto, who was a PhD student of Frederic Mott at the time, is that in the W43 protoclusters, the global CMF here, it departs from the salpeter law, okay? It is what we call top-heavy, so it is flatter. There is a higher proportion of high mass cores than expected. And this result has then been confirmed by the study of Fabien Louvet within all the protoclusters. So we still find the same behavior of a larger proportion of high mass stars. So this suggests that if the high mass end of the CMF are much flatter than is usually found, if you take the simple assumption of a coarse to star efficiency, we should have an atypical IMF for these regions. So as I said, we have several evolutionary stages, So we can now study the evolution of the CMF with the evolution of the protoclusters. So if we take back one of the first results within the W43 MM1 region, which is really young, undergoing a main burst of star formation. So the global CMF here was found top-heavy. But now, if you look at a more evolved region, so here G12, so this is a study led by Melanie Armand, who's now a postdoc in Italy. Well, this region here, it is post-burst, okay, you have some extended H2 regions, and now the CMF is no longer top-heavy, but it's salpeter-like. So we have kind of a steepening of the CMF with the evolution of the protoclusters. So you go from young massive protoclusters that shows top-heavy CMF towards evolved regions with extended H2 regions that swept the gas away. So maybe you have a second generation of cores that is forming, but only low mass cores, okay? So you have clearly a difference between young and evolved protoclusters. But now, if we want to investigate no more the global CMF, but the prestellar and the protostellar CMF, what you first need to do is to classify the cores between prestellar and protostellar stages. So during my PhD, I developed a systematic method to identify protostellar outflows and classify cores between prestellar and protostellar, which is a combination of 2 tools. The first one is a spectral one, which is the comparison of the spectra on the source with the spectra of its environment. So we call it the on-minus-off method, and we combine it with molecular outflow maps. So it strongly relies on the accretion ejection process, which is if there is a protostar inside the core there, then we must see an outflow coming out of it. So if we take as an example the core 3 here, which seems to drive a beautiful bipolar outflow with the blue lobe on the left and the right one on the right, the red one on the right, sorry. Now what we want to do is to verify that this core is indeed driving the outflow. So to do so, we compare the spectra on the source here with the spectra of its environment in an annulus, and this is what we have. So here I only show the CO line, but we also use a SIO tracer. And so if you look at the spectra on the source here, you see the beautiful line wings at high velocities representative of the bipolar outflow. Now, if you investigate the off spectra here, it only shows some slight emission in the red part. And now what you want to do is to work with the on-minus-off spectra. So you subtract this spectra to this one, and you still see these beautiful line wings. So you can now say that this core is indeed protostellar and is actually driving this outflow. And using this method, we actually identified 266 protostellar cores out of 960. So this is a paper in preparation with Tomanoni. And using this classification, we can now actually build CMF prestellar and at prestellar and protostellar stages with much larger statistics than before. So this is what we found. So this is a really preliminary result. So again, with Tom Anoni, we recently had a permanent position in France. Here you can see in blue the prestellar CMF and in red the protostellar one. And so what we found is that the prestellar CMF is salpeter-like, while the protostellar CMF is much flatter, so it's top heavy. Okay, so first thing interesting, here we confirm the results of Tom Anoni 2 years ago that were only done in the W43 protoclusters. So we confirm this result of a top heavy protostellar CMF and the salpeter prestellar-like with much larger statistics, okay? So this strongly suggests that actually the cores are being gas-fed during the protostellar stages and grow much more in mass during this protostellar stage. And one also interesting result that we have is that whenever it is a young intermediate or evolved regions, we always have a prestellar CMF that is steeper than the protostellar one. So now also what we can do using the identification, of course, and the method that I presented just before, is we can search for high mass prestellar cores. So these cores are really the cores that contain the initial conditions for high mass star formation. And using this method, we actually identified during my PhD a new and the first sample of high mass prestellar cores within the ALMA IMF survey. So we have 30 prestellar cores with a mass greater than 8 solar masses, and within them we have 12 that we call high mass, 12 cores with a mass greater than 16 solar masses. Okay, so a few statistics between 8 and 50 solar masses, between 1,000 to 4,000 AU, and really high density sources, so between 10 to the 6 to 10 to the 8. So if you look at this plot here, so core mass in function of core size, the first thing that we are going to look at is this purple core here, cores here, sorry. And here you can see that these were the previous high mass prestellar cores that were known before this work. So maybe for the first time here, we are really probing the high mass regime of the prestellar phase. And the second thing that we can see is that in blue here you have the clustered core, so a high number of massive neighbors, and in red you have the isolated ones, so less massive neighbors. And above this threshold of 16 solar masses, you can see that most of the cores are actually clustered, okay? So the most massive cores tend to be located in the central parts of the protoclusters where most of the mass is actually located. While when you look at the lower masses cores, it's much more homogeneous. You have really a mix between clustered and isolated cores. So this is interesting because we have a dichotomy, a difference in the regime between the most massive ones and the lower mass ones. And so what can we do with these prestellar cores? Well, we can now, as this is the first statistical sample, we can now derive the statistical lifetime of the high mass prestellar phase. So what you do is that you use a formula, which is you divide the number of prestellar cores by the number of protostellar ones, and you assume a protostellar lifetime. And then you place your candidates in an histogram in several bins of mass. So in blue here, you have the prestellar cores, and in red and yellow, you have the protostellar ones, and you apply the formula, and you can see the lifetime on the second y-axis with the cyan stars here. And what we find is that this lifetime ranges between 150 kiloyears to 50 kiloyears. So the first interesting result is that this lifetime is actually shorter than the low mass prestellar phase lifetime, okay, which is of around 1 million years. So this was expected because we knew that these cores were rare, but also because the high mass regime seems to be really dynamical, so you need to have a lot of gas that is accreting in short times. But when you compare this lifetime with the free-fall times, okay, these lifetimes are always greater than 10 free-fall times. And this is really surprising, not like this, because it means that there is a stop of the collapse. Okay, we need for additional support against gravitational collapse to justify for those really long lifetimes. Okay, and basically those supports could be either turbulence or magnetic support. So we investigated the turbulence in this course in order to answer are the cores stable, and we used these two optically thin lines to derive the turbulence in the cores. And then you compute the parameter alpha of the virial theorem, and you check if the cores are indeed stable thanks to turbulence. So above 1 here, we may have the first observation of high mass prestellar cores that are stable thanks to turbulence, okay? And what we see once again is that these cores tend to be located in clumps, okay? So where most of the mass is located and also most of the turbulence. But now, for these cores here, which is actually 2/3 of the sample, the turbulence is not enough to stabilize them, okay? So if turbulence is our only non-thermal support here, these cores are actually collapsing. And these cores are also located in isolated environments. So we have, once again, a dichotomy between these two regimes. So for these cores here that are not stable thanks to turbulence only, there could be an additional magnetic field. So if you use the virial theorem, you have basically, you can basically compute the magnetic field strength needed to stabilize them, and it should be between 5 and 50 milligauss. So 5 milligauss, it's already observed in high mass cores, but 50, no. So this is really interesting, and this actually leads to my current postdoctoral project, which is a study of the magnetic field and doing a full virial analysis of the dense cores of W43mm1. And we will be able normally to answer the question for the high mass prestellar cores in W43mm1, is indeed or not the magnetic field strength really important in these cores? And so I will leave you with these takeaway messages. I'm already over time, but the 3 main points are the young and massive protoclusters show CMF that departs from the salpeter law, so top heavy CMF. We have a difference between the protostellar CMF and the prestellar ones, so protostellar CMFs tend to be top heavy and prestellar ones tend to be salpeter-like. And we derived a new sample of high mass prestellar cores that need to be further studied and will be and is actually be studied, and especially on the non-thermal support parts, but also we have to investigate the cause of fragmentation. Thank you very much.
This is awesome. This is such important work, and it was a really beautiful talk. And I am going to be mean and ask the question that I think everyone else is also wanting to ask. What about binary?
Yeah, I know. That's why the last few words are here, cause of fragmentation.
Yes.
So we know that Nazar showed it at higher resolution, the cores, some of the cores, let's say, are subfragmentating. So we are sure, and actually I have a spare slide, I think. Yeah, okay. This is W43mm1. We have high resolution data in it, okay? So here you have 1, 2, 3, and 4. These are the 4 prestellar cores, high mass prestellar cores of my sample in this region. And when you look at high angular resolution data, okay, so let's say between 300 to 50 AU. Core 6 here, which was maybe the most well-known high mass prestellar core, it's actually fragmentating into 3 fragments, but for the 3 other ones, they seem to stay simple fragments. So we need to investigate that. If indeed all the cores are fragmentating, well, the high mass regime is no longer high mass, but I showed that probably in the protostellar phase, you have some feeding of mass that help to grow more in mass. So yeah, we need to investigate the cause of fragmentation. So we need high angular resolution data, with ALMA. Yeah, but I don't really have an answer.
So way back more than a decade ago now, Rao and Smith first showed that high mass stars form by accretion from a distance, not just their own core, but they accrete across the surrounding cloud. And those flows aren't necessarily at terribly high density until they hit the core. Could you be missing accretion onto these long-lived objects because it's just flowing in at low density from the environment? Because accretion would be a great way to keep an object around for more than a free fall time.
Yeah, so actually I don't have it right there. I have some preliminary results of, so first we have the V-shapes that Amy showed. So indeed we know that all these protoclusters are really dynamical with some convergent flows, and we totally agree with that. So basically what we propose here is a kind of view between the core turbulence scenario and the clump-fed. So we think that there is a clump-fed view, okay? We have dynamical convergent flows that feed the cores in mass, but we also suggest that we could have some cores which are turbulent and which are growing in mass. Like it's not either white or either black.
Accretion makes turbulence. Ibanez, Mejia et al. And myself showed that back in 2016. You drive the turbulence with the accretion. But the turbulence can't support it. That's holding yourself up by your bootstraps.
Yeah, I agree.
Forming the turbulence, that's a sign of accretion rather than a opposition to it.
Yeah, I do agree. Like, so you say turbulence is driven, and yeah, I totally agree. So we kind of see that in the ALMA MF protoclusters. So we strongly think that thanks to high accretion rates and large accretion rates, we inject turbulence into the cores that help to support them against the gravitational collapse.
Oh,
no?
The accretion is the gravitational collapse.
Yeah, I agree. I agree with this, but
okay, we should talk about this later, probably.
Last word, I think, of the conference.
So for your pre-stellar cores that you look at with higher resolution data, are you consider those stellar, or are the fragments dense enough to be forming stars?
Okay, so actually we don't know. What we suppose is that, so there is two kind of views. Let's say if you see them at really high resolution, some people will say that it's disk because it's really high density. But actually, even if there is 3 fragments here, we should see an outflow if they were indeed protostellar, because the high accretion rates tend to be high outflow rates. So, and we know that there is a lot of gas around these fragments. So the outflows should be interacting with the outwards material. So we should see actually an outflow. So either they are truly prestellar or really at the onset of the protostellar stage where the outflow is really, really small and not really powerful, and we miss it with the sensitivity that we have. Right.
Okay, let's thank our speaker again. And I'm signing off.
You can start giving
This has been a delight, a true delight. Thank you all so much for coming and for doing such good presentations, for having such dynamic, interesting talks. It's been amazing. It's also been incredibly difficult to summarize. And I have gotten the pleasure of trying to do that. So I will fail, but I will try. And hopefully I'll give you some directions to go or some ideas about how we can take what we've been working on over the last week and keep this energy going. And I can soft shoot for at least another 11 seconds. The reason this presentation is so big is you guys have so much cool stuff in your talk, so I blame you. All right, all right, so I'm not going to try to cover all of this, starting with the 3-dimensional interstellar medium in stars, going through absorption of starlight, going through the dynamic ISM. I'm sorry I've replaced the baseball with rain. Stellar deaths, chemical enrichment, feedback, stars in their environment, star clusters and their formation, and protostars. I was totally enthralled by protostars. This is not my world, but I was completely enthralled by all your talks on this. And I think it epitomizes the Inter+Stellar world. I guess I can slides. Yeah, I like to wander around. One thing I've learned is that JWST is absolutely transforming these fields. I swim in the Super Space Telescope, but I've actually never been much of a JWST person myself. I mostly do larger things, but I sort of thought, oh, well, all this talk of JWST is about where I am, and I'm aware of the selection bias, the Malmquist bias that I have of my own institute. But boy, we had talks from around the world highlighting what amazing things has been done with this telescope. I think one key thing, and those people who built this telescope knew this before, that this combination of PA emission that we're able to use to trace the dust, but also the ability to see through the dust, has really allowed us to combine these two things, to combine the stars and the gas in a way in nearby galaxies. And of course, the high resolution, this is the classic story many of us get ejected out of the galaxy into nearby galaxies as the resolution starts to match as these telescopes get bigger. So there's been a continuous story of this over decades upon decades, but many of us are feeling that wind out of the galaxy and nearby things that end in NGS, things, fangs, etc. A thing I want to exhort you, and a thing I think we've learned, is that this science matters on its own. I'm showing you here the small Magellanic Cloud, and I'm telling you that this is not just a high Z analog. Small Magellanic Cloud is very interesting in and of itself. Understanding our nearby galaxies, understanding how star formation works, understanding how stars interact with gas, how gas forms stars, this complex cycle is itself a thing. We do not have to appeal to flashier fields that are sometimes around us. It was pointed out to me that this is the first truly interstellar medium conference that's been a symposium at Space Telescope Science Institute. In 2012, there was one on cosmic flows that certainly had lots of interstellar medium in it, but I think it's really important for us to remember that this work is important in and of itself. Similarly, this is the very near the sun, and this isn't just about planets. This isn't just about planets being bathed in the interstellar medium. We heard about this at the very beginning of the conference. I'll just tell you a fun little anecdote. This is from Seth's talk. Seth and I were both working on the local interstellar medium 15 years ago, and then we both realized we needed to get jobs. And so he started working on planets and how astrospheres interact with planets, and I started working on galaxies. Now we have jobs, but I think that's kind of selling out the really important work that's being done by everybody in this room. So remember, we shouldn't necessarily just be turning to these external communities. We should be turning to each other and working together to build up the science case for the kinds of really exciting stuff that we've been seeing all week. All right. From an extremely zoomed out view, I think the era of chaos is maybe coming a little bit to a close. There's been this period of, we see a cloud and we say it looks like a duck, and I'm going to write, maybe it is a duck, to return to this duck theme. Or we see, some cluster, and we're going to go study that cluster, but out of its context. I'm showing you here Benjamin's work showing where if you have stars and you have gas together, you can trace out the H-alpha sky really, really beautifully. I'm showing the fire simulation here where you're studying both the stars and how they're interacting. And I'm showing here the young stars with the background of the gas all together in a nearby galaxy. And I think this era of synthesis, because we have enabled this joint locality, we know where things are. And part of that is being able to see through the dust, so you can really see the clusters where they are, but being able to see the clusters with that gas. Again, this is the pause plus transparency game that JWST enables. The 3D you heard at the very beginning of the conference, all this 3D stuff where we're able to use the stars to find the dust, and they're able to put the stars into that world together and see them all simultaneously. Beautiful work. Again, at the beginning of the conference. And then we're definitely seeing this in simulations. Here I'm showing you fire, but this is true in Silicon and Tigris and lots of other simulations, some of which we're showing here, some of which we're not, where we're being able to model these things simultaneously and getting down to the scale of individual stars, individual clusters, and seeing how they all interact. So this era of synthesis, I think, is really exciting. And we're being able to sort of come around the end for the first time. So I want you to all be looking out for that, all the opportunities for that coming forward. The synthesis requires a huge breadth of expertise, and I want to talk about something that we did not hear almost anything about, which is the 99% of all of the ridiculous work that all of you do for this. This kind of work involves an enormous amount of data reduction and analysis and pipelines and tools. We heard a little bit about it. I don't probably have to tell you how much work and computational effort goes into simulations to make them work. All of this, deep brains work. The Bayesian inference that goes into making these 3D dust maps, the information field theory, the scattering that Hannah was talking about. This is really hard technical work, and you cannot be an expert in all of these things at once. That is incredibly hard to do, right? Just the pretty pictures, sure, you can put them next to each other, but to really get down and make these things happen, it's impossible to have all that expertise. So this requires teamwork. an enterprise teamwork, not only across discipline, but also across fields between people who are experts in, identifying a YSO and someone who is an expert in using all of that information to create a 3D map. And I think, what I want to push you towards is to spend time with the people that you've met here and build trust. Had a great conversation with a colleague here who mentioned that first you have to build trust so that then you can have some candor. I think one of the great things that we've had during this meeting is a lot of friendliness and a lot of connection, and that's great. But I think as this community builds more trust, we can also have a little bit more candor. I personally, for me, the relationships I've built in these communities over the last too long, the greatest ones have been ones of candor, where we've been able to say, I'm really glad you're digging into this, and I think you're wrong, and I'm going to tell you why, but it's not because I don't like you. It's because I really care about you, and so I really exhort you to build trust so that we can continue to build candor. Another thing that I think is pretty clear is that junior scientists are leading the way, and it makes me really happy. I heard a few times from a few different people, there's very little gray hair in this room. And maybe it's just our excellent hair care. The truth of the matter is all of the abstracts for all the contributed talks were done blind. We're done, dual anonymous. So, it was the SOC that looked at all these talks and just picked the best ones. And that's why you have a lot of young people here who are really spending their energy to write good abstracts and come up with good ideas and present them. So I think that's great. But I don't want you to forget that senior scientists have some of the great questions. One of the problems with our literature is that we don't just say, I don't know why, and publish that. There's very little of that. And those questions are in the minds of some of the senior scientists here who have been thinking about these questions for lots and lots of decades. And so the young people here who've been leading, who have all these answers, don't forget to go back to some of us little crotchety people and ask, what are the questions that you think are still unanswered, that are still missing? So there's a great opportunity for more information. Lots of opportunities for excellence. We also have opportunities for excellence in acronyms. A lot of great acronyms. I know I left off ACEs. I know I left off a few. I went through as fast as I could to find them. And I really feel like we are leading the way now with made me so happy. But anyway, yes, just to leave that there. And then, I think I'll just I would love for you to come back and visit sometime. The Interstellar Medium Group, ISM-STAR at SDSCI, is a lot of people. This is not even all of us, although we've got some graduates here too. We've got typically about a dozen postdocs, graduate students, lots of different PIs working on different things across a lot of the disciplines you heard here today. And it was during group meeting of that group that this idea came up, this came up with, and then we all said, Liz, you should definitely lead that. That would be a great idea. We'll support you in leading that. But yeah, we have group meetings every week. We have this low density universe group that spans an even larger group. And please come back and give talks. Please apply for jobs. We'll be posting jobs. Please come join us. We're really having a great time. And we love having you all here. So thank you very much. And I'm going to turn this over to Liz.
Yeah, thank you. Before we fully close out the symposium part and move to Hack Day, I just think it's super important to thank all the people that made the symposium possible. And I really want to shout out Chris. Chris, I would like you to stand up. We've really been working on this symposium together, the two of us, and it's just been such a joy to work with him and figure out how to classify all of your abstracts in a way that made sense with an interdisciplinary conference.
Thank you for making my life so hard.
And it's just been such a joy to work with him, and he's done a large amount of the work too. So I just want to show a lot of appreciation for him, as well as the entire SOC. We had to classify over 200 abstracts and read them all, and it's just been so lovely to see all of the science that we've heard this week. It's really just been such a joy. It's like one very, very long ISM star group meeting in the best of ways.
Thank you for letting us trick you into coming to our group meeting.
Yes. So I want to thank all the members of the SOC. All their names are here, especially all the people that could make it in person and for all of the efforts that you all made chairing. I really appreciate it. And I also want to highlight the amazing work the LOC did, and I'd just like to name names. So thank you, Kirsten, for setting up the awesome welcome reception wine and for setting up SDAS on Wednesday and making everyone those delicious food. I want to thank Hannah for dealing with the absolute mess that is the baseball game. I want to thank Steve and Adam for running the posters and running the discussions. And of course, Eric and Christina, who will be your Hack Day people. And lastly, before I turn it over to your Hack Day people, a huge shout out to Shamaya, who's been at the front of the hall over there. You've walked by her every day. The events planning group at Space Telescope is incredible, and almost all the logistics that you guys have this week is because she is incredible at her job. So huge.
And the AV team as well.
Oh, and the AV team, of course, of course. Thank you, AV team. Thank you in the box. So I really have just had so much fun this week, and I really encourage you to think about all the takeaways that Josh mentioned, that this does not have to be just 1 week, and I'm really looking forward to continue working with a lot of you on different projects and to continue the spirit that we've created at this conference back at your own institutions and in your future collaborations. So thank you all so much. I can turn it over to Eric and we can start to do some Hack Day stuff.
First, I think we all have to give Liz a humongous round. Then I can take over.
Show anything?
Just one quick thing. I'll take care of it. All right. So, an era of chaos in the ISM might be ending, but the era of chaos in this room is just beginning. Hopefully, organized chaos, but if not, that's fun too. So, let's see what we want to do. We have like 5 minutes until lunch. We might stretch that a little, but. What I think we want to do right now is first let anyone who didn't have a chance to give a hat pitch yesterday come up now and do that. That could be nobody, or it could be a bajillion people. So let me actually just get a show of hands. Is there anybody who wants to give a hack pitch right now? If the answer is no, that is perfectly fine. That would be Christina's 4th hack pitch. So I think we'll give everyone else a chance before Christina.
Yeah, I don't want to.
Is there someone who's being voluntold? Is that what I'm seeing over here? So whoever's being voluntold, are you accepting the voluntoldtion? Okay. Oh yeah.
So I've talked to a number of people this week about this idea, but if you, my pitch, I guess, how does this work?
You just say you think it's a good idea. Yeah.
Yeah, I am wanting to scope out a project that I want to do to, like take some resolved star clusters and unresolve them and see what happens when we compare that to stellar models. So if you are interested in sketching that out with me, that's my pitch. Yeah.
I hope that leads to a paper title like Unresolved Clusters or Unresolving Clusters, because that I would read that. Is there anybody else who has a pitch they want to give other than Christina? Ah, back there. Ah, wait. This is Mordecai like the 5th. I think Christina. Yeah.
So let me actually extend my pitch, having had conversations with some of you. I suggested installing Torch and learning how to run star cluster simulations. But a variation on that would be learning how to read
the existing public data that we have already made available to the community. And that might be a more tractable project, particularly for someone who's perhaps primarily an observer or off in some other area of our collective phase space, but would still allow access to the data and perhaps comparisons to observations. So if we could just add that to my pitch, really, as data files from existing simulations.
Sounds good. Thanks, Mordecai, the fourth and a half. Anyone else have a pitch they want to give? All right, we'll let Christina, the fourth, fifth, third, whatever it is, go ahead.
Down here at the bottom, I thought about it this morning, but there's been a lot of talk about clearing timescales for different clusters and environments, simulation and observationally, and there's even counterexamples. I think, Becca, you in your superstar cluster, like they're not clearing their environment, and it's a lot of different, we think. And so it seems like at this point there's sort of a consensus that in most scenarios they're clearing their environment, and there's a bunch of different galactic properties going on and a lot of different metallicities. And I think it would be great to, like, anyone who has any results of, you know, some cluster clearing some environment, if we could like collect all of that information and put it on a plot as a function of like how long has the feedback been going, what is the like mass of the molecular cloud, you know, how many feedback sources are there in this cluster, and have supernova gone off yet, and sort of try to accumulate as many statistics, because a lot of times these sort of independent case studies, because it takes a lot of work to do. And so I think it'd be really cool to culminate that information. Anyway, so that's my pitch.
Is worth highlighting that someone who gives 4 different ideas doesn't have to do those 4 ideas. So if you're inspired by any of these ideas that Mordecai or Christina have said, you should feel comfortable approaching them and being like, I want to lead that idea. That is, in fact, some of the best hacks I've ever seen were ideated by one person and then run by another group of people. That can work really well. Any other hack pitches anyone wants to do right now? We have to wait until we feel a little awkward and our stomachs are grumbling.
I guess, sorry. So I think, Liz, did you do the Prima one?
Yeah, I talked about it, but you should talk about it too.
I feel like if anyone wants to write a geo case for Prima, that could be a good afternoon activity. I feel like you could crank it out probably in an hour or two, especially with someone there to help with any of the technical stuff. So I'm happy to lead that. Also, just as like motivation, I think the Prima stuff is really exciting, and like we're working super hard to make an awesome proposal, but word on the street is like the NASA administrators, like they really care about the community part, and like we have very little control of that. So like showing that the community cares, putting in cases is huge, and like will not happen without community. So pressure.
Our one last thing is that Karen has to leave a little early today during the afternoon, and so we're gonna start a little early, and we have a corner of the cafe set aside for this. So we're gonna have a lunchtime during lunch, talking about this and general knowledge sharing to kind of pre-game the actual hack session to make the best use of Kara's valuable time.
And then, but then in the afternoon, it's going to be still in Cafe Con, right?
TBD. The director's office has taken the Cafe Con room from us for some amount of time.
Okay, we'll work this out later. Yeah. Okay. So one last bit of logistics before you're all released for lunch. One is that lunch is a great time to like talk to people about you're going to do your hack thing. Don't feel like you're banned from speaking about hacks during lunch. Several of the pre-organized, the people who submitted early have been assigned rooms that are not accessible without an access card. So what we're all going to do is we're going to come back here after lunch at 1:40, I think is what the schedule says. Yeah, 1:40. And then for the people who are running sessions that are in the places where you have to scan a card, you want to come here, you go into the corner with whoever that is. They'll go to their rooms, Priya, wherever you are. I will get you to your room because you probably don't have an access card. I don't know if she's here right now, but I'll take care of that. Everyone else, I think, has a card, but you'll have to join them to get there. And then for all of the other hacks, we can either be, we have this room still the whole time, right? Yeah, either in here or in the cafe. Both are great hacking spaces. Cafe is a little better because you can face each other, but there's also lots of room in this room. So with that, go forth and eat and think about hacking.
Someone else is going to put that aside.
Doing it right now.
We're putting it on the side.
I keep forgetting.
Good job.